What if we took the billionaire who tweets about Dogecoin at 3 in the morning, builds rockets in his backyard, and genuinely believes he can turn humanity into a multiplanetary species, and actually put him through the ultimate stress test by placing him on every single planet in our solar system, plus some of the most fascinating alien worlds we've discovered beyond our cosmic neighbourhood, starting with the safest destinations and building up to that red planet he has been obsessing over for the past 20 years. You know, when I realised that Elon has spent decades planning Mars colonies while never actually experiencing what it feels like to step outside on even our closest celestial neighbour, it gave me the most wonderfully mischievous scientific inspiration for tonight's cosmic adventure. This is Science for Sleep, where we transform the most ambitious space fantasies into peaceful bedtime explorations, and I am your devoted sleepy scientist, absolutely delighted to help you fall asleep fast while we embark on the most entertaining planetary survival experiment ever conceived. Before we begin, if you enjoy these cosmic journeys, please like, subscribe, and hit that hype button if you see it. Tell me in the comments where you're listening from and your strangest dream ever. Your support means the world to me and helps this channel keep exploring the cosmos together. Let's begin. Now, I should probably mention that our imaginary experiment comes with all the necessary safety precautions because, let's be honest, most planets in our solar system are actively trying to kill anything that dares to visit them. Our brave volunteer is equipped with the finest SpaceX technology money can buy, an unlimited supply of whatever snacks billionaires prefer, and most importantly, a direct communication link back to mission control here on Earth, where a team of brilliant engineers are monitoring his every vital sign and ready to extract him the moment things get more interesting than a Twitter flame war. This might be too fascinating for sleep, I should warn you, because we're about to discover exactly why Earth is the only planet where you can casually step outside in your pajamas without immediately facing 17 different ways to meet your cosmic demise. We will explore worlds where the very air would dissolve your lungs in seconds, where atmospheric pressure would crush you like stepping on a grape, where radiation levels would cook you from the inside out, and where the temperature swings make the most extreme Earth weather look like a gentle spring afternoon. But we are going to approach this journey with the gentle curiosity of explorers rather than the anxiety of survivors, letting each world teach us something profound about the delicate miracle that makes life on Earth not just possible, but absolutely extraordinary. And along the way, we will discover that our planetary tourist, despite all his engineering genius and technological advantages, is fundamentally just another fragile human being, no more capable of surviving the harsh realities of space than any of us listening tonight in our comfortable beds. Our cosmic adventure begins not with the dramatic spectacle of Mars or the crushing hellscape of Venus, but with something much more familiar yet still profoundly alien, our faithful moon, that ancient companion that has watched over human civilization since our earliest ancestors first gazed up at the night sky and wondered what secrets lay hidden in that pale, crater-marked face that changes shape with mysterious regularity. The moon represents humanity's first serious attempt to leave the protective embrace of Earth's atmosphere, and it seems only fitting that we begin our experiment here, in this place where 12 human beings have already walked and lived to tell about it. When our space entrepreneur steps out of his custom-designed starship onto the lunar surface, he finds himself in a landscape that is simultaneously the most familiar and most alien place in the entire solar system. Picture Elon, encased in his specially designed SpaceX suit that probably costs more than most people's houses, taking his first steps onto the same powdery regolith where Neil Armstrong left footprints that remain undisturbed after more than 50 years. The silence that greets him is more complete than anything he's ever experienced on Earth, a silence so absolute that it seems to have weight and presence, because sound simply cannot exist in the vacuum that surrounds him on all sides. Every word he speaks into his communication system travels not through air molecules vibrating against each other, but through radio waves that leap instantly across the void to reach mission control back on Earth. This creates an eerie sensation of disconnection from the normal world of human experience, where speech and hearing follow rules that no longer apply in this airless realm. The temperature on the moon swings between extremes that would challenge even the most advanced thermal regulation systems ever designed. During the lunar day, which lasts about 14 Earth days because the moon rotates so slowly, the surface temperature climbs to nearly 400 degrees Fahrenheit, hot enough to melt lead and certainly hot enough to turn any unprotected human being into a very expensive piece of space jerky in a matter of minutes. But during the equally long lunar night, temperatures plummet to nearly minus 400 degrees Fahrenheit, cold enough to freeze the carbon dioxide in your breath solid if you are somehow able to breathe in this environment. The lack of atmosphere means there is nothing to moderate these temperature swings. No gentle blanket of air to distribute heat and cold the way Earth's atmosphere does so beautifully and invisibly every moment of our lives. Our entrepreneurial explorer, standing in this magnificent desolation, represents all of human ambition concentrated into a single fragile biological form. His suit works constantly to maintain a comfortable 72 degrees Fahrenheit around his body, while the ground beneath his feet shifts between these temperature extremes that would instantly kill any known form of life. Every breath he takes has been carefully processed and recycled by machinery that must function perfectly in an environment designed to destroy electronics. Every drop of water has been precisely rationed because there are no rivers or rain clouds or morning dew on this ancient world. Every calorie of energy stored in his suit's batteries represents the difference between continued existence and becoming a permanent lunar monument to human overconfidence. But here is what makes the moon almost charming compared to the destinations that await us later in our journey. The gravity here is gentle, almost playful. At 1/6 of Earth's gravitational pull, our space tourist can move with an almost balletic grace that would be impossible back home. Each step becomes a slow-motion leap that carries him farther than any human step has a right to go, creating a sense of superhuman ability that must feel intoxicating after a lifetime of being anchored to Earth's more demanding gravitational field. The low gravity transforms even the most mundane activities into something magical. Dropping a tool means watching it fall in slow motion, giving you plenty of time to reach out and catch it before it hits the ground. Jumping means soaring through the vacuum in graceful arcs that would make professional dancers weep with envy. Even walking becomes a kind of dance as each footfall propels you forward in gentle bounds across the ancient landscape. The real danger on the moon is not immediate death from atmospheric poisoning or crushing pressure, but rather the gradual accumulation of small challenges that could overwhelm even the most advanced life support systems. The fine lunar dust called regolith has been pulverized by billions of years of meteorite impacts into particles so sharp and abrasive that they can cut through the strongest materials humans have ever devised. This dust gets into everything with the persistence of the universe's most annoying houseguest. It clogs air filters, scratches helmet visors, works its way into the moving parts of equipment, and slowly degrades the systems that keep our explorer alive. Unlike Earth dust, which has been worn smooth by wind and water over millions of years, lunar dust retains all the sharp edges created by cosmic impacts, making it incredibly destructive to anything mechanical or electronic. Think about that for a moment as you settle deeper into your comfortable bed tonight. The moon tries to kill visitors not with dramatic violence like some cosmic action movie, but with patient, persistent erosion of the technology that keeps them alive. Every breath our entrepreneur takes removes a tiny amount of oxygen from his limited supply. Every movement generates heat that his cooling systems must dissipate. Every hour that passes brings him closer to the point where his carefully balanced life support systems will no longer be able to maintain the delicate bubble of habitability that surrounds him. Yet compared to what awaits him on our next destinations, the moon feels almost welcoming. Here, at least, the dangers are well understood and manageable with current technology. The Apollo astronauts proved that humans can live and work on the lunar surface for days at a time, conducting experiments, driving rovers, collecting samples, and even playing a little golf in the low-gravity environment. Though I suspect our modern space entrepreneur would probably try to live stream the entire experience on social media if the communication delays did not make that impractical. The real beauty of our moon adventure lies not in the technical challenges of survival, but in the profound psychological shift that comes from standing on another world and looking back at Earth. Our entrepreneur, for all his tweets about making life multiplanetary and his confident projections about Mars colonization timelines, experiences something that no amount of engineering brilliance or financial success can prepare him for. From the moon, Earth does not look like the center of the universe or the inevitable launching point for cosmic expansion. It looks like what it truly is, a tiny oasis of warmth and life suspended in an ocean of cosmic indifference that stretches in every direction toward infinity. The atmosphere that he has taken for granted his entire life appears as the thinnest possible shell around our planet, so delicate that it seems miraculous that it exists at all. Every cloud swirling in Earth's atmosphere, every blue ocean reflecting sunlight, every green continent dotted with the lights of human civilization, every person he has ever met or argued with on the internet exists within that fragile bubble visible from his lunar vantage point. The perspective shift is profound and immediate, a visceral understanding that all of human history, all of our wars and loves and scientific discoveries and works of art have taken place within that small blue marble hanging in the infinite of black. This transformation of perspective represents one of the most important psychological gifts that space exploration offers to human consciousness. When you see Earth from space, the arbitrary borders that divide nations become invisible lines on an indivisible whole. The conflicts that seem so important from ground level fade into insignificance against the backdrop of cosmic emptiness. What remains is a stunning recognition of our shared vulnerability and our absolute dependence on the thin layer of air and water that makes our planet habitable. Our space entrepreneur's first day on the moon passes in a series of carefully planned activities designed to test both his equipment and his ability to adapt to this new environment. He conducts experiments that could easily be performed by robots, but the real experiment is him, testing how a human consciousness adapted for Earth's conditions responds to the profound alienness of life beyond our atmosphere. He learns to move in the low gravity, discovering that even simple tasks like picking up objects or changing direction while walking require completely different techniques than those developed over a lifetime on Earth. He learns to trust his life support systems completely, understanding that his continued existence depends not on his own biological resilience, but on the perfect functioning of machines designed and built by other human beings. As the hours pass and Earth continues its stately rotation in the lunar sky, a deeper understanding begins to settle into his consciousness. This is what it truly means to be multiplanetary, not the grand vision of cities and commerce and interplanetary civilization that he has described in countless presentations and interviews, but the immediate visceral reality of being utterly dependent on technology for every breath, every heartbeat, every moment of continued existence. The moon teaches him, and us, that survival beyond Earth is not just an engineering challenge to be solved with better rockets and more efficient life support systems. It represents a complete transformation of what it means to be human, a fundamental shift in our relationship with the natural world that has shaped every aspect of our evolution over millions of years. Every natural instinct that has kept humans alive throughout our species' history must be carefully examined and often completely abandoned. The simple act of breathing becomes a complex negotiation with recycling systems and atmospheric processes. Sleep must be planned around equipment maintenance cycles and communication windows with Earth. Even the most basic human functions like eating and waste elimination require careful consideration of closed-loop life support systems and resource conservation. The food that sustains him during his lunar stay has been carefully selected, not just for nutrition, but for its ability to be stored, prepared, and consumed in a zero-atmosphere environment where the normal rules of cooking and digestion no longer apply. Water recycling systems process not just drinking water, but every drop of moisture from his breath and perspiration, creating a closed loop of liquid that must be maintained with obsessive precision. As our imaginary lunar mission draws toward its conclusion, our entrepreneur has gained something far more valuable than another achievement to add to his impressive resume of space-related accomplishments. He has experienced firsthand the profound humility that comes from surviving entirely through the grace of human engineering and technological precision, understanding in his bones rather than just his intellect what it truly means to be a fragile biological organism in an environment that wants nothing more than to eliminate him from existence. The preparation for departure from the moon represents a bittersweet moment, the end of humanity's gentlest introduction to the realities of interplanetary survival. As he takes his final steps across the lunar surface, our space tourist carries with him not just rock samples and scientific data, but a transformed understanding of what his Mars colonization dreams actually entail in terms of human psychological adaptation and technological dependence. The moon has been kind to him, offering challenges that are manageable with current technology and dangers that can be mitigated with careful planning and engineering excellence. The low gravity has made him feel superhuman, the familiar sight of Earth has provided psychological comfort, and the successful track record of previous lunar missions has given him confidence that humans can indeed survive and work in this environment. But now, as we prepare to launch him toward his next destination, the stakes begin to rise dramatically in ways that will test not just his technology, but his fundamental assumptions about the feasibility of human survival beyond Earth. Mars, the planet that has captured his imagination and consumed billions of dollars of his company's resources, awaits with challenges that make the moon's gentle hostility seem like a peaceful garden. The journey from Moon to Mars represents more than just a change of destination. It represents a leap from the merely difficult to the genuinely dangerous, from conditions that challenge human technology to conditions that actively seek to destroy anything humans might build. Our space tourist, settling into his starship for the months-long journey between worlds, has time to contemplate what he learned during his lunar adventure and prepare mentally for challenges that make the moon look like a peaceful vacation resort. Mars greets arriving spacecraft with an atmosphere that is simultaneously too thin to breathe and too thick to ignore, creating a perfect storm of survival challenges that have frustrated mission planners and destroyed more than half of all robotic missions ever sent to the Red Planet. The approach to Mars requires navigating this atmospheric contradiction with precision that pushes spacecraft design to its absolute limits. As our entrepreneur's starship begins its descent through the Martian atmosphere during the complex entry, descent and landing sequence that has claimed so many previous missions, he experiences firsthand the engineering nightmare that has made Mars exploration one of the most difficult challenges in all of space exploration. The thin atmosphere provides just enough resistance to heat incoming spacecraft to dangerous temperatures, but not nearly enough to slow them down for a safe landing without additional systems. This means that every Mars landing becomes a carefully choreographed dance between heat shields that must withstand temperatures hot enough to melt copper, parachutes that must deploy perfectly in an atmosphere less than 1% as dense as Earth's, and rocket engines that must fire with split-second timing to bring the spacecraft to a gentle touchdown on the surface of an alien world. But let us assume that our imaginary landing goes perfectly, with all systems functioning exactly as designed and our space entrepreneur stepping out onto the rusty surface of Mars, the planet he's dreamed of colonizing since he first founded SpaceX with the explicit goal of making life multiplanetary. The landscape that greets him is both magnificent and terrifying, a vista of red plains and ancient impact craters stretching towards horizons that seem impossibly distant under a sky the colour of butterscotch candy. The first thing he notices is the silence, even more complete than what he experienced on the moon because Mars's thin atmosphere cannot carry sound waves the way Earth's dense air does so effortlessly. When he speaks into his communication system, his words travel only a few feet through the tenuous air before being absorbed by the near vacuum that passes for an atmosphere on this ancient world. The wind, when it blows with enough force to create planet-spanning dust storms, is fierce enough to lift particles into the thin air, but too weak to pose any real physical threat to his pressurized suit. Mars operates under a completely different set of physical rules than the Earth that gave birth to our species. The atmospheric pressure at the Martian surface is less than 1% of what we experience at sea level on our home planet, roughly equivalent to the pressure at an altitude of 100,000 feet above Earth, well beyond the Armstrong limit where exposed bodily fluids begin to boil at body temperature. This means that without his pressurized suit maintaining Earth-like conditions around his body, our entrepreneur's blood would literally begin to boil within seconds, a phenomenon known as ebullition that would cause rapid decompression sickness and death within less than 2 minutes. The saliva on his tongue would bubble and foam, the moisture in his eyes would begin to vaporize, and the air in his lungs would expand violently as the pressure differential tried to turn his respiratory system inside out. The temperature on Mars swings wildly throughout both the day and the seasons, creating thermal challenges that make spacecraft thermal management incredibly complex. Even at its most pleasant, During summer at the equator, when conditions are as good as they ever get on Mars, the temperature rarely rises above 70 degrees Fahrenheit, and that only for brief periods during the warmest part of the day. During the Martian winter at the poles, temperatures plummet to nearly minus 200 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the atmosphere and create the seasonal polar ice caps that expand and contract with the changing seasons. These temperature swings create atmospheric dynamics that can generate dust storms covering entire continents, storms that can last for months and completely obscure the sun for weeks at a time. But it is not just the cold and the low pressure that make Mars dangerous for human explorers, it is the radiation environment that represents perhaps the greatest long-term threat to anyone attempting to establish a permanent presence on the red planet. Unlike Earth, Mars has no global magnetic field and only a whisper of an atmosphere to protect its surface from the constant bombardment of cosmic rays and high-energy particles from the Sun. Over the course of a year on Mars, which lasts 687 Earth days, our space entrepreneur would receive roughly 100 times the radiation dose considered safe for nuclear workers on Earth. This level of exposure significantly increases the risk of cancer, damages the immune system, and can cause cognitive impairment that would make the complex problem-solving required for survival on Mars increasingly difficult over time. As Elon explores the Martian landscape during his planned stay on the surface, he begins to understand why his ambitious plans for Mars colonization have always seemed so optimistic to the broader scientific community. Every breath he takes comes from his suit's life support systems, which must function perfectly in an environment where the slightest malfunction could be fatal. Every calorie of energy must be carefully rationed because there are no backup systems, no emergency services, no possibility of rescue if something goes fundamentally wrong. The Martian soil itself presents unique challenges that go far beyond the simple absence of Earth-like conditions. Composed largely of iron oxide, the same compound that causes rust on Earth, the regolith gives Mars its characteristic red colour, but also makes it incredibly difficult to work with for any kind of construction or resource extraction. The soil is highly alkaline and contains compounds called perchlorates that are toxic to human life and corrosive to most metals. These perchlorates, which make up about 0.5% of Martian soil by weight, would contaminate any water extracted from the ground and make growing food in native Martian soil impossible without extensive chemical treatment. Any attempt to establish a self-sustaining settlement would require either importing vast quantities of clean soil from Earth, which is obviously impractical, or developing complex chemical processing systems to neutralize the toxins in the native regolith. Water, the fundamental requirement for any human settlement, exists on Mars but not in easily accessible forms that would make colonization straightforward. The polar ice caps contain vast amounts of frozen water mixed with frozen carbon dioxide, but they are located thousands of miles from the most promising landing sites near the equator, where solar power generation would be most effective and temperatures would be most moderate. Underground, Mars likely harbours significant amounts of liquid water in aquifers that could potentially be tapped, but accessing this water would require drilling technology that has never been tested under Martian conditions. The water itself might be highly saline or contaminated with the same perchlorates that make the surface soil toxic, requiring extensive purification before it could be used for drinking or agriculture. Think about the profound irony of our entrepreneur's situation. As he stands on the surface of the planet he has spent years describing as humanity's backup plan. He has developed the most advanced rocket technology in human history, capable of carrying massive payloads across interplanetary distances with unprecedented efficiency and reusability. Yet here on Mars he finds himself utterly dependent on the few cubic feet of habitable space contained within his environmental suit. All of his wealth, estimated in the hundreds of billions of dollars, all of his engineering genius that has revolutionized multiple industries, all of his ambitious dreams about making life multiplanetary and ensuring the long-term survival of human consciousness, come down to this single moment of profound vulnerability on a world that operates according to physics rather than human ambitions or financial resources. The Martian day, called a sol, lasts about 24 hours and 37 minutes, tantalizingly close to Earth's rhythm but just different enough to constantly remind him that he is operating according to alien rules that care nothing for human biological clocks or business schedules. As the butterscotch sky darkens towards sunset, he watches the sun shrink to roughly 2/3 the size it appears from Earth, a pale reminder of just how far he has travelled from the warmth and light that make life possible. During the Martian night, the temperature drops so rapidly that carbon dioxide begins to freeze out of the atmosphere, creating a light snowfall of dry ice that would be beautiful if it were not so potentially deadly to any exposed equipment. The stars, unobscured by a thick atmosphere, shine with a clarity that makes Earth's night sky seem cloudy by comparison. Two small irregular moons, Phobos and Deimos, race across the starfield in orbits so low and fast that they complete multiple cycles each Martian night. Phobos, the larger of Mars's two moons, appears to rise in the west and set in the east because it orbits so quickly that it actually moves faster than Mars rotates. This creates the surreal experience of watching a moon race backward across the sky, completing more than 3 orbits in a single Martian day. The sight would be fascinating if our entrepreneur were not constantly reminded that these rapid orbital mechanics are possible only because Mars lacks the gravitational strength to capture more substantial moons like Earth's. Our space entrepreneur's time on Mars becomes a meditation on the meaning of profound isolation and the psychological challenges of being further from Earth than any human has ever travelled. He is separated from his home planet by millions of miles of empty space and months of travel time, with no possibility of rescue or emergency evacuation if his life support systems fail or his mental health deteriorates under the stress of absolute solitude. The communication delay between Mars and Earth ranges from 4 to 24 minutes depending on the relative positions of the planets, making real-time conversation impossible and forcing him to adapt to a new form of human interaction based on carefully composed messages sent across the void. Every email, every video call, every request for technical support must be planned, with the understanding that the response will not arrive for at least 8 minutes and often much longer. This communication lag creates a profound sense of disconnection from the human community that has shaped every moment of his life up to this point. The casual back and forth of normal conversation becomes impossible, replaced by a more formal exchange of information that lacks the spontaneous warmth of immediate human contact. Even his most urgent questions must be answered by his own knowledge and problem-solving abilities, because help from Earth arrives too late to be useful in emergency situations. But perhaps the most profound lesson Mars teaches him is about the true meaning of sustainability and resource management on a scale that makes his previous business ventures seem simple by comparison. On Earth, he could afford to think in terms of rapid growth, exponential scaling, and revolutionary disruption of existing markets. On Mars, survival depends on careful conservation, meticulous planning, and absolute reliability of every system and subsystem. Every piece of equipment must work perfectly for years without the possibility of replacement parts or repair services. Every gram of food and water must be accounted for and recycled with obsessive efficiency. Every decision must be evaluated not just for its immediate consequences, but for how it might affect survival prospects months or years in the future when conditions might be very different. The Red Planet forces him to confront the difference between entrepreneurial optimism and the harsh realities of interplanetary survival that operate according to the laws of physics rather than market dynamics or human ambition. Mars does not care about his timeline for establishing a self-sustaining colony, his projections for passenger capacity on future missions, or his dreams of terraforming the planet to make it more Earth-like. Mars simply exists, indifferent to human plans and desires, governed by atmospheric dynamics and geological processes that have been operating for billions of years according to their own implacable logic. The planet's beauty is real and spectacular, but it is the beauty of an alien world that was never designed to support life as we know it. A world that will kill any visitor who makes even small mistakes in planning or execution. As his planned stay on Mars draws to a close, our entrepreneur faces the psychological challenge that every Mars explorer will eventually confront, the recognition that this beautiful, terrible world could easily become his permanent resting place, despite all of his preparation, technology, and confidence in human ingenuity. Mars has shown him that survival here is not a given but a constant struggle against an environment that offers no margin for error or mechanical failure. The return journey to Earth, which will take many months even with the most efficient transfer trajectories, gives him ample time to process what he's learned during his brief but transformative stay on the surface of Mars. The red planet has provided him with insights far more valuable than any scientific discovery or technological breakthrough, a visceral understanding of what it truly means to be human in a universe that was not designed for human life. But our cosmic adventure has only just begun to reveal the true diversity of planetary environments that exist within our solar system. Mars, for all its challenges and hostility, represents only the middle tier of planetary danger in our local cosmic neighborhood. As we prepare to launch our intrepid space explorer toward destinations that make Mars look like a gentle training ground, we enter realms where the very concept of human survival becomes almost theoretical. Venus, our next stop, awaits with conditions so hellish that they challenge the fundamental assumptions underlying any spacecraft design intended to operate for more than a few hours. The planet that ancient astronomers called the morning star and evening star, not realizing they were observing the same object, hides beneath its beautiful clouds an environment so hostile that it has destroyed more spacecraft than any other destination in the solar system. The journey from Mars to Venus takes our entrepreneur through the inner solar system, where solar radiation intensifies and space becomes increasingly hostile to the electronics and life support systems that keep him alive. The months-long cruise between planets gives him time to reflect on how profoundly his understanding of space colonization has evolved since leaving Earth what seems like a lifetime ago. The optimistic timelines and confident projections that characterize his public presentations about Mars settlement now seem almost naive compared to the visceral reality of depending on technology for every breath, every heartbeat, every moment of continued consciousness. The business plans and passenger manifests and economic models that look so convincing in corporate boardrooms bear little resemblance to the immediate challenges of keeping a single human being alive in environments where every natural process works against biological survival. Venus begins as a bright point of light against the starfield, growing slowly larger over the weeks of approach until it resolves into a brilliant white sphere wrapped in thick, featureless clouds that completely obscure the surface beneath. From space, Venus looks almost Earth-like in its size and brightness, earning it the nickname Earth's twin from astronomers who did not yet understand the hellish conditions that those beautiful clouds conceal. The approach to Venus requires navigating not just the planet's intense gravitational field, but also its corrosive atmosphere and crushing surface pressure that make landing more technically challenging than anything he's previously experienced. The descent through Venus's atmosphere becomes a race against time as his specially designed spacecraft fights to maintain structural integrity against conditions that would destroy most materials within minutes of exposure. The atmospheric composition of Venus reads like a chemical weapons manual, designed by a malevolent cosmic intelligence. 96% carbon dioxide creates a runaway greenhouse effect that traps solar heat with terrifying efficiency, while clouds of concentrated sulfuric acid float through the atmosphere at altitudes where Earth's commercial aircraft normally cruise. These acid clouds are not the gentle water vapor clouds of Earth, but concentrated chemical solutions that would dissolve most metals and plastics long before the surface pressure could crush them. The surface pressure on Venus is 92 times greater than Earth's atmospheric pressure at sea level, equivalent to being more than half a mile underwater in our planet's deepest oceans. This crushing pressure would instantly collapse any conventional spacecraft hull and compress the human body in ways that are difficult to imagine and impossible to survive. But the pressure is only the beginning of Venus's assault on anything brave enough to attempt a landing on its surface. The temperature at ground level reaches 900 degrees Fahrenheit, hot enough to melt lead, zinc, and many other metals that are commonly used in spacecraft construction. This temperature is actually hotter than Mercury's surface, despite Venus being nearly twice as far from the Sun, a testament to the incredible efficiency of the planet's greenhouse effect. As our entrepreneur's spacecraft descends through the increasingly dense atmosphere, external sensors begin registering conditions that push every engineering system to its absolute breaking point. The sulfuric acid in the atmosphere starts eating away at any exposed materials, while the rising temperature threatens to overwhelm even the most advanced cooling systems ever designed for space exploration. The atmospheric pressure increases exponentially with depth, creating a crushing embrace that threatens to implode the spacecraft long before reaching the surface. By the time his specially designed lander finally touches down on the Venusian surface, our explorer finds himself in what can only be described as a technological version of hell, surrounded by conditions that make Mars seem like a tropical paradise. The landscape visible through his spacecraft's reinforced windows glows with the dull red heat of an oven interior, while instrument readings confirm surface conditions that exist at the very limits of what any human technology can withstand. The atmospheric pressure outside his vehicle is equivalent to having multiple elephants standing on every square inch of the spacecraft's hull, creating stress loads that threaten to crush even the strongest materials ever developed. Venus forces our entrepreneur to confront the ultimate limits of human technology and engineering ambition in ways that make his previous challenges on the Moon and Mars seem manageable by comparison. Unlike those worlds, where survival is difficult but possible with careful planning and advanced technology, Venus represents a fundamental challenge to the very concept of human exploration and the assumption that sufficiently advanced engineering can overcome any environmental obstacle. The thick atmosphere that creates Venus's hellish surface conditions also produces some of the most spectacular and terrifying atmospheric phenomena in the solar system. Lightning bolts flash continuously through the acid clouds with energies that dwarf any electrical storm on Earth, creating displays of raw power that would be beautiful if they were not so utterly deadly to any electronic systems unfortunate enough to be exposed to them. The atmospheric dynamics generate winds in the upper atmosphere that reach speeds of over 200 miles per hour, creating a superrotation effect where the atmosphere circles the planet much faster than the planet itself rotates. These high-altitude winds carry the sulfuric acid clouds around the planet in just 4 Earth days, even though the planet itself takes 243 Earth days to complete a single rotation. Our entrepreneur's time on Venus is necessarily measured in hours rather than days or weeks, as his spacecraft's systems begin to succumb to the planet's relentless assault on anything that was not forged in the fires of hell itself. The extreme conditions make any form of extended exploration impossible with any technology that could conceivably be developed using known materials and engineering principles. But even these few hours on the surface of our nearest planetary neighbour provide profound insights into the extraordinary range of conditions that can exist on worlds that appear similar to Earth when viewed through telescopes from a comfortable distance. Venus teaches him that similarity in size and orbital position means absolutely nothing when it comes to habitability or the prospects for human survival. The runaway greenhouse effect that transformed Venus from a potentially habitable world into the furnace that greets modern explorers began billions of years ago when the planet's slightly closer position to the Sun caused its oceans to evaporate more rapidly than Earth's. Water vapor is itself a greenhouse gas, which caused temperatures to rise further, which caused more water to evaporate, creating a positive feedback loop that eventually boiled away Venus's entire water supply and left behind the acid-wrapped hell that challenges our spacecraft today. This lesson in planetary climate evolution carries profound implications for our understanding of how atmospheric systems can undergo irreversible changes when pushed beyond critical tipping points. Venus represents a cautionary tale about what can happen to any planet where greenhouse gases accumulate beyond the point where natural regulatory mechanisms can maintain stable conditions. The escape from Venus requires every bit of our spacecraft's remaining capability, fighting against the intense gravitational field and corrosive atmosphere that seem determined to add our explorer's mass to the planet's already substantial bulk. As the spacecraft finally breaks free from Venus's embrace and climbs back toward the relative safety of interplanetary space, the contrast between the planet's violent environment and the peaceful emptiness of the vacuum becomes almost jarring. The damage inflicted by Venus on the spacecraft's systems serves as a permanent reminder of just how hostile planetary environments can be to anything designed and built for Earth conditions. Protective coatings have been stripped away by acid exposure, electronic systems have been stressed by extreme temperatures, and structural components show signs of the incredible pressures they have endured during the brief visit to this hellish world. But our cosmic journey is far from complete, and the challenges ahead will test not just our explorer's technology, but his fundamental understanding of what constitutes a planetary environment suitable for any form of exploration. The gas giants of the outer solar system await with conditions so alien and extreme that they will force him to completely reimagine the concepts of landing, exploration, and survival that have guided every previous step of his interplanetary odyssey. Before we subject our brave entrepreneur to the mind-bending challenges of the outer solar system, however, we should take a detour to some of the most fascinating destinations that modern astronomy has revealed beyond our local cosmic neighbourhood. The exoplanets discovered by missions like Kepler and TESS have shown us that the universe contains worlds so varied and exotic that they make our solar system's planets seem almost boring by comparison. TRAPPIST-1, a red dwarf star system located about 40 light-years from Earth, has become one of the most studied planetary systems in modern astronomy, precisely because it offers what might be our best chance of finding conditions suitable for life as we know it. This system contains 7 rocky planets, all roughly Earth-sized, with 3 of them orbiting within their star's habitable zone, where liquid water could theoretically exist on their surfaces. The journey to TRAPPIST-1 would require propulsion technology far beyond anything currently available, involving travel times measured in decades or centuries, even with the most optimistic projections for future spacecraft development. But for the sake of our thought experiment, let us imagine that our space entrepreneur has access to some form of advanced propulsion that can carry him across the interstellar void to experience firsthand what it might be like to visit truly alien worlds. TRAPPIST-1, E, the 4th planet in the system, and perhaps the most Earth-like world yet discovered, greets our interstellar traveller with conditions that are simultaneously familiar and utterly foreign. The planet receives roughly the same amount of energy from its red dwarf star as Earth receives from our Sun, but the light itself is redder and dimmer, creating a perpetual twilight atmosphere that would make photography impossible without artificial lighting. The most striking feature of the TRAPPIST-1 system is how tightly packed the planets are compared to our solar system. All 7 worlds orbit closer to their star than Mercury does to our Sun, creating gravitational interactions between planets that cause their orbital periods to change over time in complex patterns that astronomers are still working to understand. This close proximity means that from the surface of TRAPPIST-1e, the other planets in the system would appear as disks in the sky, rather than points of light, creating spectacular views where multiple worlds would be visible simultaneously during certain orbital alignments. Some of these neighbouring planets would appear larger than our Moon does from Earth, creating a sky that changes dramatically as the complex orbital dance proceeds. The red dwarf star that provides energy to this system is much smaller and cooler than our Sun, which means that planets in the habitable zone must orbit much closer to receive adequate warmth for liquid water. This proximity creates the likelihood that most or all of the TRAPPIST-1 planets are tidally locked, meaning they always show the same face to their star, just as our Moon always shows the same face to Earth. Tidal locking creates extreme environmental conditions that have no parallel in our solar system, with permanent day and night sides that experience vastly different temperatures and weather patterns. The day side of TRAPPIST-1e might maintain temperatures suitable for liquid water, while the night side could be cold enough to freeze carbon dioxide from the atmosphere, creating a world where the climate zones are determined not by latitude, but by proximity to the subsolar point. The boundary between the day and night sides, called the terminator zone, would experience eternal twilight conditions where temperatures might be moderate enough to support liquid water and possibly even life. This terminator zone would be a narrow band circling the planet where the temperature gradient between the scorching day side and the frozen night side creates complex atmospheric dynamics unlike anything found on Earth. Atmospheric circulation on a tidally locked world would be dominated by massive convection cells that transport heat from the day side to the night side, creating winds that could reach velocities far exceeding anything found in our solar system. These heat transport mechanisms would be essential for maintaining habitable conditions, but they would also create weather patterns so violent that they might make the planet uninhabitable despite being in the correct orbital zone for liquid water. The red dwarf star at the centre of the TRAPPIST-1 system presents its own unique challenges for any potential life on these worlds. Red dwarf stars are known for producing powerful stellar flares that can increase their brightness by factors of 10 or more for periods lasting from minutes to hours. These flares emit intense ultraviolet and X-ray radiation that could strip away planetary atmospheres over geological timescales. Our entrepreneur's visit to TRAPPIST-1e would require protection not just from the alien atmospheric conditions, but from radiation levels that could be thousands of times higher than anything experienced in our solar system when the star decides to unleash one of its periodic fits of electromagnetic fury. The magnetosphere that protects Earth from solar radiation might not exist on these worlds, leaving their surfaces exposed to the full force of stellar particle bombardment. The possibility of life on TRAPPIST-1e remains one of the most tantalizing questions in modern astrobiology, but any organisms that might exist there would have to be adapted to conditions radically different from those that shaped evolution on Earth. They would need to survive in perpetual twilight or darkness, cope with extreme temperature gradients, and endure radiation levels that would quickly kill most terrestrial life forms. But perhaps the most profound lesson that TRAPPIST-1e teaches our interstellar explorer is about the incredible diversity of planetary environments that exist throughout the galaxy, and the humbling recognition that Earth-like conditions might be far rarer than our optimistic projections for finding habitable worlds have assumed. Even planets that meet the basic criteria for habitability, existing in the correct orbital zone around a stable star with the right mass and composition, can harbour conditions so alien that they challenge our fundamental assumptions about what makes a world suitable for life. The return journey from TRAPPIST-1 to our solar system would provide our entrepreneur with months or years of travel time to contemplate the vast differences between the worlds he has now visited and the profound challenges that face any species attempting to expand beyond its planet of origin. Each world has revealed new categories of environmental hostility and new ways that planetary physics can create conditions inimical to biological survival. Yet the diversity of worlds he's experienced also suggests that the universe might contain environments so varied and extreme that some of them could support forms of life based on entirely different chemical and physical principles than those that govern terrestrial biology. The search for life beyond Earth might require expanding our definitions of habitability to include conditions that would instantly kill any organism evolved for Earth's gentle environment. As our cosmic adventurer returns to our solar system for the next phase of his planetary tour, he carries with him a transformed understanding of humanity's place in the universe and the extraordinary challenges that face any civilization attempting to become truly multiplanetary. The worlds he's visited have each taught him something essential about the relationship between technology and survival, between human ambition and physical reality, between the dreams of space exploration and the harsh constraints imposed by the laws of physics. Jupiter looms ahead in the darkness, a banded giant whose great red spot alone is larger than the entire Earth, promising new lessons in the fundamental alienness of worlds that operate according to principles so extreme they seem to belong to the realm of science fiction rather than planetary science. The gas giants represent a completely different category of astronomical object, worlds without solid surfaces where the very concepts of landing and exploration must be completely reimagined. The approach to Jupiter begins to reveal the planet's true nature as something far more complex and dangerous than the images in astronomy textbooks might suggest. Even from millions of miles away, Jupiter's radiation environment begins to affect spacecraft electronics, providing a preview of the electromagnetic punishment that awaits any technology brave enough to venture into the planet's immediate vicinity. Jupiter's magnetosphere extends for millions of miles in every direction, creating an invisible bubble of trapped charged particles that would be instantly fatal to any unprotected biological organism. This radiation environment is so intense that it has limited the operational lifetime of every spacecraft that has attempted to study the planet from close range, gradually degrading Alaris' electronic systems and solar panels until they cease to function. The planet itself grows from a point of light to a disk, then to a sphere so large that it begins to fill the entire field of view as the spacecraft approaches. The famous bands of clouds that give Jupiter its distinctive appearance resolve into incredibly complex weather systems, storms larger than Earth that have been raging for centuries, winds that reach speeds capable of destroying any aircraft ever built for terrestrial conditions. As our entrepreneur's spacecraft begins its descent into Jupiter's atmosphere, he experiences something that no human has ever experienced before: the sensation of falling through a gas giant's endless sky where there is no ground rushing up to meet him, no horizon line to provide spatial orientation, just an endless deepening of atmospheric density as his vehicle plunges toward the planet's mysterious core thousands of miles below the cloud tops. The upper layers of Jupiter's atmosphere are relatively benign compared to what awaits deeper in the planet's gravitational embrace, composed mostly of hydrogen and helium, with traces of methane, ammonia, and water vapor that create the colorful bands visible from space. But as the descent continues through increasingly dense atmospheric layers, the pressure begins to build exponentially while temperature rises from the crushing weight of the entire atmosphere above. At this point in his journey, our space entrepreneur must confront a fundamental question that challenges every assumption about planetary exploration developed during humanity's brief experience with rocky worlds. What does it mean to visit a planet that has no surface, no solid ground to walk on, no clear boundary between the planet itself and the space that surrounds it? Jupiter forces him to reimagine basic concepts like landing and exploration that have guided every previous step of his cosmic odyssey. The atmospheric pressure continues building as his descent progresses, reaching levels that begin threatening the structural integrity of even his specially designed spacecraft. The hydrogen and helium surrounding his vehicle become denser and denser, transitioning from gas to liquid to exotic states of matter that exist nowhere else in the solar system except perhaps in the cores of other gas giants. Temperature climbs steadily as gravitational compression heats the atmospheric gases to levels where the distinction between his spacecraft's climate-controlled interior and the increasingly hostile environment outside begins to blur. Somewhere far below his current position, perhaps thousands of miles beneath the cloud tops, lies Jupiter's core, a ball of rock and metal compressed to densities that create pressures millions of times greater than anything found on Earth's surface. The journey toward that unreachable core would require travelling through regions where hydrogen becomes metallic under extreme pressure, where atoms themselves are crushed into configurations that can only be studied theoretically in terrestrial laboratories. These conditions create materials with properties so exotic that they seem to belong more to the interior of stars than to anything we might recognize as a planetary environment. The Great Red Spot, Jupiter's most famous atmospheric feature, reveals itself during the descent as a storm system of unimaginable violence and scale. This hurricane-like vortex has been raging continuously for at least 300 years, possibly much longer, with no signs of weakening or dissipating. The entire Earth could fit comfortably inside this single storm, which generates winds exceeding 300 miles per hour and creates turbulence that would instantly destroy any aircraft designed for Earth's gentle atmosphere. But the Great Red Spot represents only one of countless storm systems that churn through Jupiter's atmosphere in patterns that dwarf any weather phenomenon ever recorded on Earth. Lightning bolts flash through the clouds with energies thousands of times greater than terrestrial thunderstorms, creating electrical discharges that could power entire cities if they could somehow be harnessed and transmitted across the vast distances of space. The atmospheric dynamics of Jupiter operate according to principles that make Earth's weather system seem almost quaint by comparison. Heat from the planet's interior drives convection currents that extend thousands of miles vertically through the atmosphere, creating circulation patterns that involve more energy than humanity has ever produced throughout its entire history of technological civilization. As our entrepreneur's spacecraft is gradually overwhelmed by Jupiter's atmospheric embrace, he experiences a form of dissolution that is uniquely cosmic in its scale and violence. The planet does not simply destroy his vehicle through mechanical failure or component breakdown, but rather incorporates it into the vast atmospheric machine that has been processing matter and energy for billions of years according to its own inexorable logic. The hydrogen and helium that now surround his disintegrating spacecraft will eventually be compressed and heated until they undergo nuclear fusion deep in Jupiter's core, the same process that powers stars and provides the energy that makes life possible throughout the universe. In a very real sense, Jupiter represents a failed star that never quite achieved the critical mass necessary to ignite sustained nuclear reactions, but which retains many characteristics that make stellar environments so hostile to biological life. But let us allow our imaginary explorer to escape Jupiter's grasp through the magic of thought experiments, emerging from his encounter with new understanding of what it means to explore worlds that exist at the very limits of human comprehension. Jupiter has taught him that the universe contains phenomena so alien and extreme that they challenge fundamental assumptions about what constitutes a world suitable for any form of exploration, using technology based on human understanding of materials and engineering. The gas giants represent an entirely different category of astronomical objects that simply cannot be studied using the same techniques that work for rocky worlds like Mars or Venus. They require completely new approaches to space exploration, new technologies that have yet to be developed, new concepts of what it means to visit and study another world when that world has no solid surface and operates according to physical principles that have no parallel in human experience. Saturn awaits with its magnificent ring system and its own collection of atmospheric extremes that will test our entrepreneur's understanding of what constitutes the limits of planetary environments. The ringed planet presents navigation challenges unlike anything found elsewhere in the solar system, while its atmospheric conditions create some of the most spectacular and dangerous weather phenomena known to modern astronomy. The approach to Saturn requires threading through a cosmic obstacle course of ice and rock particles that orbit the planet in bands stretching for hundreds of thousands of miles in every direction. These ring particles, ranging in size from tiny ice crystals to boulders larger than buildings, move at orbital velocities of tens of thousands of miles per hour, meaning that collision with even the smallest fragment could punch through the strongest spacecraft armor ever devised. The rings themselves tell a story of cosmic violence and gravitational mechanics operating on scales that dwarf any engineering project ever attempted by human civilization. Each particle represents the remains of moons or asteroids that ventured too close to Saturn's gravitational field and were torn apart by tidal forces, creating a debris field that has been spread into these magnificent bands through billions of years of orbital dynamics. Navigation through the ring system demands precision that pushes spacecraft guidance systems to their absolute limits, requiring real-time adjustments to avoid collisions with debris moving at hypersonic velocities. The beauty of the rings, viewed from within the system itself, creates light displays and shadow effects that have no parallel anywhere else in the known universe. But this beauty comes with the constant threat of instantaneous destruction from impacts with ring material. Saturn's atmosphere presents its own unique challenges that build upon the lessons learned during the encounter with Jupiter, while introducing new categories of extreme weather and atmospheric chemistry. The planet's lower overall density compared to Jupiter creates different patterns of atmospheric circulation, but these differences make survival no less challenging for any technology designed to operate in the crushing depths of a gas giant atmosphere. The famous hexagonal storm at Saturn's North Pole comes into view during the atmospheric descent, revealing a geometric weather pattern so precise and regular that it seems artificial rather than natural. This six-sided formation maintains its shape across distances larger than Earth's entire diameter, persisting for decades without any apparent external force to maintain its geometric perfection. The winds within Saturn's atmosphere achieve velocities that make even Jupiter's most violent storms seem gentle by comparison, with jet streams circling the planet at speeds approaching 1,000 miles per hour. These are not mere breezes, but atmospheric rivers carrying energy equivalent to thousands of nuclear explosions, yet they maintain their structure and direction with a stability that has persisted for centuries of telescopic observation. As our space entrepreneur descends deeper into Saturn's atmospheric embrace, he encounters phenomena that challenge his understanding of what weather can be under conditions that exist nowhere in terrestrial experience. Lightning bolts flash through the methane and ammonia clouds with energies that dwarf any electrical storm ever recorded on Earth, creating electromagnetic pulses that could disable electronic systems from thousands of miles away. The temperature and pressure profiles within Saturn's atmosphere follow patterns similar to Jupiter's, but with subtle differences that make survival even more challenging for any spacecraft attempting extended exploration. The lower density means that vehicles fall faster through the outer atmospheric layers, building up velocities that must somehow be dissipated before the increasing pressure crushes any conventional spacecraft design. Saturn's extensive moon system adds another layer of complexity to the exploration challenge, with dozens of natural satellites ranging from tiny irregular asteroids to world-sized bodies like Titan, which harbours its own thick atmosphere, and methane lakes that create a frozen parody of Earth's hydrological cycle. These moons create gravitational perturbations that affect spacecraft trajectories in ways that must be constantly calculated and adjusted. Enceladus, one of Saturn's smaller moons, erupts geysers of water ice from its south polar region, providing evidence of a subsurface ocean that might harbour conditions suitable for life. These ice geysers create a tenuous atmosphere around the moon and contribute material to Saturn's ring system, demonstrating the complex interactions between planetary bodies that make the Saturn system a dynamic environment rather than a static collection of orbiting objects. The escape from Saturn's gravitational influence requires navigation through the same ring system that made approach so hazardous, but now with spacecraft systems potentially damaged by the extreme conditions encountered in the planet's atmosphere. The complex gravitational field created by Saturn's many moons creates regions of orbital instability that could trap a spacecraft or send it careening into one of the ring planes with devastating consequences. Uranus presents our entrepreneur with the next stage of his education in planetary extremes, introducing him to a world that operates according to rules so bizarre that they seem to violate basic principles of planetary formation and evolution. This ice giant rotates on its side like a cosmic barrel rolling through space, creating seasonal patterns and magnetic field orientations that have no parallel anywhere else in the solar system. The approach to Uranus reveals a planet that appears to have been knocked off its cosmic axis by some primordial collision that sent it tumbling into an orientation that defies conventional understanding of how planets should behave. Its magnetic field, ring system, and moon orbits all follow patterns that seem to ignore the normal rules governing planetary systems, creating navigation challenges that require completely new approaches to spacecraft guidance and orbital mechanics. The cold at this distance from the Sun transcends anything our explorer has previously experienced, reaching temperatures where even the most advanced heating systems struggle to maintain equipment functionality. Solar energy becomes essentially irrelevant as a power source, forcing complete dependence on nuclear power systems that must operate reliably for years without maintenance in an environment where component failure means certain death. Uranus's atmosphere presents conditions that are simultaneously less immediately destructive than the crushing hellscapes of Jupiter and Saturn, yet more alien in their fundamental characteristics. The lower pressures and temperatures create an environment that kills through gradual attrition rather than immediate violence, slowly draining heat and energy from any technology until life support systems simply cease to function in the relentless cold. The methane in Uranus's atmosphere gives the planet its distinctive blue-green colour, while creating weather patterns that operate according to chemical processes unknown anywhere else in the solar system. Methane clouds form and dissipate according to rules that govern the behaviour of substances at temperatures where most materials would be frozen solid, creating atmospheric dynamics that seem to operate in reverse compared to terrestrial meteorology. The bizarre magnetic field orientation creates charged particle interactions that produce auroras appearing at random locations, rather than concentrating near the poles like they do on every other planet. These electromagnetic phenomena suggest internal processes operating according to principles that planetary scientists are still working to understand, making Uranus a laboratory for studying physics under conditions that cannot be replicated anywhere on Earth. Neptune, the most distant of the giant planets, greets our space explorer with winds that represent the fastest atmospheric phenomena in the solar system, somehow generating jet streams that exceed 1,000 miles per hour, despite receiving less than 1% of the solar energy that drives Earth's much gentler weather systems. These supersonic winds exist for reasons that challenge current understanding of atmospheric dynamics and planetary energy budgets. The deep blue colour of Neptune creates visual beauty that seems impossible given the planet's hostile environment and tremendous distance from any source of warmth or light. The methane absorption that creates this spectacular coloration also indicates atmospheric chemistry operating under conditions so extreme that they provide insights into fundamental processes governing the behaviour of matter under exotic temperature and pressure regimes. the Great Dark Spot and other storm systems visible in Neptune's atmosphere, appear and disappear over time, scales measured in years rather than centuries, suggesting atmospheric dynamics far more volatile and energetic than those governing the more stable storm systems of Jupiter and Saturn. These rapid changes indicate energy sources and circulation patterns that remain mysterious to planetary scientists studying the planet through telescopic observations. Our entrepreneur's descent into Neptune's methane-rich environment takes him into atmospheric chemistry that operates according to rules unknown anywhere else in the solar system. Methane snow falls through layers of hydrogen and helium, while exotic ice crystals form and sublimate according to thermodynamic processes that exist only under the extreme conditions found in the outer reaches of planetary atmospheres. The combination of crushing pressure, extreme cold, and reactive atmospheric chemistry creates an environment that systematically destroys any technology designed for operation under terrestrial conditions. Neptune represents the ultimate test of engineering capabilities, demanding perfection from every system while providing conditions that make such perfection impossible to achieve or maintain. But Neptune also provides perhaps the most profound lesson about the incredible diversity of planetary environments that can exist even within a single star system. This distant, beautiful, hostile world maintains enough internal energy to generate weather systems more violent than anything found on planets much closer to the Sun's warmth, suggesting energy sources and atmospheric processes that operate according to principles still being discovered by planetary science. The escape from Neptune marks the end of our explorer's tour of the giant planets, but his cosmic education is far from complete. Each gas giant has revealed new categories of atmospheric extremes and gravitational phenomena that expand the catalogue of conditions under which planetary environments can operate. The diversity of worlds within our own solar system suggests that the universe contains an almost infinite variety of planetary types, each operating according to its own unique combination of physical laws and environmental factors. The outer solar system has taught our entrepreneur that human space exploration will require not just improvements in propulsion and life support technology, but fundamental advances in understanding how to design systems that can operate under conditions so extreme they challenge basic assumptions about materials, science, and engineering. The temperature extremes, pressure differentials, radiation environments, and chemical compositions encountered among the gas giants represent only a small sample of the challenges that await any species attempting to explore the full diversity of worlds that exist throughout the galaxy. As we prepare to subject our brave space explorer to even more extreme conditions that will test the absolute limits of what constitutes a survivable environment, we must acknowledge that his journey through the gas giants has already pushed the boundaries of what might be considered possible for human exploration. Yet ahead lies a destination so hostile that it makes all previous challenges seem like gentle preparation for the ultimate test of technological capability and human endurance. The Sun awaits our local star, a nuclear furnace so powerful that it has been converting matter into energy continuously for nearly 5 billion years and shows no signs of diminishing its output. Solar exploration represents not just another challenging destination, but a journey into an environment where the fundamental nature of matter and energy takes on characteristics that exist nowhere else in our immediate cosmic neighborhood. The approach to the Sun begins at distances that would be considered safe for exploring any other object in the solar system, but which represent the beginning of a radiation environment so intense that it overwhelms conventional spacecraft cooling systems and gradually destroys electronic components through cumulative damage from high-energy particle bombardment. Even at Mercury's orbital distance, solar radiation flux reaches levels that require entirely new approaches to thermal management and material science. The solar wind, that constant stream of charged particles flowing outward from the Sun at velocities of hundreds of miles per second, creates a radiation environment that makes the magnetic fields of the gas giants seem gentle by comparison. Protons and electrons, accelerated to significant fractions of the speed of light, penetrate materials that would easily stop any terrestrial radiation source, gradually degrading spacecraft systems through atomic-level damage that accumulates over time. But the most profound challenge of solar exploration is not technical but conceptual, requiring our entrepreneur to confront the ultimate source of all energy that has powered every moment of biological evolution on Earth. The Sun converts 4 million tons of matter into pure energy every single second through nuclear fusion reactions operating at temperatures and pressures that dwarf any conditions found elsewhere in the solar system. The solar surface, called the photosphere, maintains temperatures of approximately 10,000 degrees Fahrenheit, hot enough to vaporize any known material instantly. But this visible surface represents only the outermost layer of a nuclear reactor that extends hundreds of thousands of miles in every direction, with core temperatures reaching nearly 30 million degrees Fahrenheit under pressures that compress matter into states having no parallel in terrestrial experience. Our space entrepreneur's approach to the solar corona, that ethereal outer atmosphere visible during eclipses, takes him into a realm where normal concepts of temperature and pressure break down completely. The corona maintains temperatures of several million degrees, despite being much less dense than the photosphere below, creating conditions that challenge fundamental understanding of how energy transfer and thermodynamics operate under extreme stellar conditions. Solar flares, those spectacular eruptions of magnetic energy that can disrupt communications throughout the solar system, become immediate threats to survival rather than distant astronomical curiosities. A single coronal mass ejection releases more energy than human civilization has produced throughout its entire technological history, creating radiation environments that would be instantly fatal to any biological organism and quickly destructive to even the most heavily shielded spacecraft. The magnetic field lines that emerge from the Sun's interior and extend throughout the solar system become visible as coronal structures that dwarf planetary dimensions, creating electromagnetic phenomena operating on scales that encompass the entire space between worlds. These magnetic field configurations channel solar particles and energy in patterns that influence atmospheric conditions on every planet and moon in the solar system. As our entrepreneur's specially designed solar probe approaches closer to the Sun than any human technology has ever ventured, he enters a region where matter exists primarily as plasma, with electrons stripped from atomic nuclei by the intense electromagnetic fields and high-energy radiation. This plasma environment operates according to magnetohydrodynamic principles that govern the behavior of electrically conducting fluids under extreme conditions. The experience of approaching the Sun becomes a journey through increasingly exotic states of matter and energy that provide insights into the fundamental processes powering not just our local star, but the billions of other stars that populate our galaxy and the trillions of galaxies that fill the observable universe. Every photon of light that has ever powered photosynthesis on Earth, every calorie of solar energy that has driven terrestrial weather patterns, originated in nuclear fusion reactions like those our explorer now witnesses firsthand. The hydrogen and helium that constitute most of the Sun's mass undergo fusion reactions that convert a small fraction of their mass directly into energy according to Einstein's equation relating mass and energy. These reactions release neutrinos that pass through matter so easily that they travel from the solar core to Earth without interacting with any intervening material, providing a direct window into the nuclear processes occurring deep within stellar interiors. But perhaps the most awe-inspiring aspect of our entrepreneur's solar encounter is the recognition that this incredible fusion reactor has maintained a remarkably stable energy output for billions of years, providing the steady stream of energy that made the evolution of complex life possible on Earth. The Sun represents the ultimate example of cosmic engineering, a self-regulating system that has operated continuously throughout the entire history of our planet. The nuclear reactions occurring in the solar core operate under conditions so extreme that they create their own category of physics, where quantum mechanical effects allow hydrogen nuclei to overcome their natural electrical repulsion and fuse together to form helium, releasing tremendous amounts of energy in the process. These fusion reactions require temperatures of at least 15 million degrees Celsius and pressures more than 200 billion times greater than Earth's atmospheric pressure at sea level. The energy produced in the solar core takes approximately 100,000 years to work its way outward through the dense stellar material before emerging as the light and heat that make life possible throughout the solar system. This means that the sunshine warming your face today was actually created when our earliest human ancestors were still learning to use stone tools, a humbling reminder of the vast timescales on which stellar processes operate. Our entrepreneur's closest approach to the sun forces him to confront the ultimate source of all energy and life in our cosmic neighborhood, while simultaneously experiencing conditions that would instantly vaporize any conventional matter. The specialized heat shield protecting his spacecraft must withstand temperatures approaching those found in nuclear reactors, while somehow maintaining enough structural integrity to protect the delicate instruments and life support systems within. The escape velocity required to break free from the sun's gravitational influence represents one of the most demanding propulsion challenges in all of space exploration, requiring speeds that approach significant fractions of the velocity of light. Our entrepreneur's departure from the solar system would mark him as the first human being to achieve true interstellar status, no longer gravitationally bound to our local star and heading toward the vast emptiness that separates our sun from its nearest stellar neighbors. But before we send our cosmic explorer into the interstellar medium, we should revisit some of the most intriguing destinations that his journey has revealed, the exotic exoplanets that represent entirely new categories of worlds operating under conditions that have no parallel in our solar system. These alien worlds offer insights into the incredible diversity of planetary environments that exist throughout our galaxy and beyond. Kepler 452b, often called Earth's cousin, orbits a star remarkably similar to our Sun at a distance that places it squarely within the habitable zone where liquid water could exist on its surface. But this apparent similarity conceals fundamental differences that make this world profoundly alien despite its Earth-like characteristics. The planet receives only 10% more energy from its star than Earth receives from our Sun, yet it is 60% larger in diameter, creating gravitational conditions that would make human exploration extremely challenging. The surface gravity on Kepler 452b would be approximately twice that of Earth, meaning that our space entrepreneur would weigh twice as much as he does on his home planet. This increased gravitational field would affect every aspect of human physiology, from cardiovascular function to bone density, creating health challenges that would make long-term survival difficult even if the atmosphere and temperature proved to be suitable for human life. The star that Kepler 452b orbits is about 1.5 billion years older than our Sun, which means it has been gradually increasing in brightness throughout its lifetime. This aging process suggests that the planet might currently be experiencing the early stages of a runaway greenhouse effect, similar to what transformed Venus from a potentially habitable world into the hellish furnace that challenges modern spacecraft. If Kepler 452b still retains its atmosphere and oceans, the increased stellar radiation could be driving water vapor into the upper atmosphere, where ultraviolet light breaks it down into hydrogen and oxygen, with the lightweight hydrogen escaping to space and leaving behind an increasingly oxygen-rich atmosphere. This process might be creating atmospheric conditions unlike anything found on Earth, with oxygen concentrations that could make the planet extremely flammable. The longer year on Kepler 452b, lasting 385 Earth days, would create seasonal patterns that differ subtly but significantly from those that have shaped terrestrial life throughout its evolutionary history. These extended seasons might drive atmospheric circulation patterns and weather systems that operate according to different rules than those governing Earth's climate, creating environments that could be habitable but profoundly alien. Our entrepreneur's visit to this Earth-like yet fundamentally different world would force him to confront the possibility that planets meeting basic criteria for habitability might still harbour conditions that make human survival extremely difficult or impossible. The search for truly Earth-like worlds might require finding planets that match not just orbital characteristics and stellar properties, but also gravitational conditions, atmospheric composition, and magnetic field strength. K218b, a sub-Neptune exoplanet located about 120 light-years from Earth, has captured scientific attention because of evidence suggesting water vapor in its atmosphere and the possibility of liquid water existing under exotic atmospheric conditions. But this world represents an entirely new category of potentially habitable planet that has no analogue in our solar system, with characteristics that challenge fundamental assumptions about what makes a world suitable for life. The planet is about 2.5 times larger than Earth, and orbits a red dwarf star at a distance that places it within the habitable zone, but its mass and composition suggest that it might be more like a mini-Neptune than a super-Earth. This means that beneath a potentially habitable surface layer might lie a thick atmosphere of hydrogen and helium that creates pressure and temperature conditions unlike anything found on terrestrial planets. Recent observations suggest that K218b might have clouds composed of water vapor in its upper atmosphere, with the possibility of liquid water existing at certain atmospheric levels even if the surface itself is uninhabitable. This creates the tantalizing possibility of aerial life forms that could exist in the atmospheric layers where temperature and pressure conditions are suitable for liquid water, even if the planetary surface is too hostile for conventional biology. The radiation environment around K218b presents its own unique challenges, as red dwarf stars are known for producing powerful stellar flares that could strip away planetary atmospheres over geological timescales. Any life that might exist in the planet's atmosphere would need to be adapted to periodic bombardment by high-energy particles and radiation levels that would quickly kill most terrestrial organisms. Our space entrepreneurs' exploration of K218b would require developing entirely new technologies for atmospheric exploration and survival in environments where the boundary between space and atmosphere becomes blurred by exotic pressure and temperature gradients. The planet represents a laboratory for studying atmospheric chemistry under conditions that cannot be replicated anywhere in our solar system. Tohei 715b, a recently discovered super-Earth orbiting within the habitable zone of a nearby red dwarf star, offers another example of how exoplanets can meet basic habitability criteria while still presenting conditions that challenge human survival. This world receives stellar energy equivalent to what Earth receives from our Sun, but its larger size and different stellar environment create a completely alien set of environmental conditions. The planet orbits its star every 19 Earth days, creating a year so short that seasonal changes would be measured in weeks rather than months. This rapid orbital period suggests that the world might be tidally locked, always showing the same face to its star and creating permanent day and night sides with extreme temperature differences. The red dwarf star that TI 715b orbits is much smaller and cooler than our Sun, which means that the habitable zone lies much closer to the stellar surface. This proximity increases the likelihood of tidal locking, while also exposing the planet to stellar flares and radiation levels that could make surface conditions extremely hostile to life as we know it. If Tohei 715b has managed to retain a substantial atmosphere despite its proximity to its active red dwarf star, the atmospheric dynamics would be dominated by heat transport between the permanent day and night sides. This could create wind systems and weather patterns operating on scales, and with intensities that dwarf any atmospheric phenomena found on Earth. Our entrepreneurs' visit to this world would require protection not just from alien atmospheric conditions, but from radiation environments that could change dramatically when the star decides to unleash one of its periodic electromagnetic outbursts. The planet represents a testing ground for understanding how life might adapt to conditions that are simultaneously Earth-like and utterly alien. Proxima Centauri EEB, the closest known exoplanet to our solar system, orbits our nearest stellar neighbour at a distance that places it within the habitable zone for liquid water. But this proximity to Earth, a mere 4.25 light-years away, conceals the fact that conditions on this world are likely to be extremely hostile to any form of life that evolved under terrestrial conditions. Proxima Centauri is a red dwarf star known for producing some of the most powerful stellar flares observed in our local stellar neighbourhood, with energy outputs that can increase the star's brightness by factors of 10 or more for periods lasting from minutes to hours. These flares emit intense ultraviolet and X-ray radiation that could sterilize any planetary surface within the habitable zone. The planet is likely tidally locked to its star, creating permanent day and night sides with temperature differences that could exceed several hundred degrees. The day side might experience temperatures hot enough to boil water, while the night side could be cold enough to freeze carbon dioxide from the atmosphere, creating extreme climate zones separated by relatively narrow twilight regions. If Proxima Centauri b has managed to retain an atmosphere despite the hostile radiation environment, the atmospheric circulation would be driven by the extreme temperature gradient between day and night sides. This could create wind systems with velocities that make terrestrial hurricanes seem gentle, while also transporting materials and energy in patterns that have no parallel in Earth's atmospheric dynamics. The magnetic field environment around Proxima Centauri b would be constantly buffeted by the stellar wind and flare activity from its red dwarf star, creating electromagnetic conditions that could interfere with any electronic systems and potentially affect biological processes in ways that are difficult to predict or mitigate. Our space entrepreneur's exploration of humanity's closest exoplanetary neighbour would require developing technologies capable of operating under radiation conditions that change unpredictably and violently, while also dealing with atmospheric and surface conditions that represent extremes not found anywhere in our solar system. WASP-121b represents an entirely different category of exoplanet that pushes the boundaries of what constitutes a potentially explorable world. This hot Jupiter orbits so close to its star that atmospheric temperatures exceed 2,500 degrees Celsius, hot enough to vaporize metals and create weather patterns involving precipitation of liquid titanium and other exotic materials. The extreme heating causes the planet's atmosphere to puff up to enormous proportions, creating a world that is larger than Jupiter despite having less mass. This inflated atmosphere extends so far from the planetary core that it is gradually being stripped away by stellar radiation, creating a comet-like tail of escaping atmospheric material that streams away from the star. The atmospheric chemistry on WASP-121b operates according to principles that have no parallel in our solar system, with temperatures hot enough to dissociate water molecules into their component atoms and create atmospheric layers where different chemical species exist in gaseous forms that would be impossible under terrestrial conditions. The day side of the planet experiences atmospheric dynamics driven by thermal radiation rather than reflected sunlight, creating an environment that glows with its own heat like a forge or furnace. The night side, while cooler, still maintains temperatures that would instantly vaporize any spacecraft designed for exploration of conventional planetary environments. Our entrepreneur's visit to WASP-121b would represent the ultimate test of high-temperature materials science and thermal management technology, requiring innovations that push beyond anything developed for solar exploration. The planet serves as a laboratory for studying atmospheric physics under conditions that exist nowhere else in our local cosmic neighbourhood. GJ-1214b, a super-Earth with a thick atmosphere that might be composed primarily of water vapour, represents another category of exotic world that challenges assumptions about planetary habitability and atmospheric evolution. This world orbits a red dwarf star at a distance that places it closer to its sun than Mercury is to ours, yet atmospheric models suggest that surface conditions might be cool enough for liquid water to exist under its thick atmospheric blanket. The planet's density suggests that it might be composed primarily of water, ice and rock, with the possibility of a global ocean existing beneath a thick atmosphere of water vapour and other gases. This creates the potential for a world where the boundary between atmosphere and ocean becomes blurred by pressure and temperature gradients that have no parallel on Earth. The atmospheric pressure on GJ-1214b might be dozens of times greater than Earth's, creating conditions where water remains liquid at temperatures that would cause it to boil away under terrestrial atmospheric pressure. This could allow for aquatic environments existing at atmospheric levels hundreds of miles above any solid surface, creating three-dimensional oceanic habitats that extend throughout the planetary atmosphere. The radiation environment around this super-Earth would be shaped by its red dwarf star's flare activity and the planet's close orbital distance, creating conditions where any potential life would need to be adapted to periodic bombardment by high-energy particles. The atmospheric chemistry might include compounds and reactions that are impossible under Earth's gentler radiation environment. Our space entrepreneur's exploration of GJ-1214b would require developing technologies for operating in high-pressure aquatic environments that exist in atmospheric rather than oceanic contexts, while also dealing with radiation conditions and atmospheric chemistry that have no terrestrial parallels. 55 Cancri e, a super-Earth that orbits so close to its star that it completes a full year in just 18 hours, represents an extreme example of how planetary environments can operate under conditions that challenge basic assumptions about atmospheric dynamics and surface geology. the planet likely experiences surface temperatures exceeding 2,000 degrees Celsius, hot enough to melt rock and create oceans of lava that cover the entire planetary surface. The rapid orbital period creates tidal forces that keep the planet's interior molten, while also causing extreme temperature variations, as different parts of the surface experience day and night cycles measured in hours rather than the 24-hour periods that have shaped all terrestrial life. These rapid thermal cycles create atmospheric dynamics and geological processes that operate on timescales having no parallel in our solar system. The atmosphere of 55 Cancri E might be composed of vaporized rock and metals, creating weather patterns where it literally rains molten silicon and other refractory materials. The atmospheric chemistry would involve phase transitions between solid, liquid, and gaseous states of materials that remain solid under all terrestrial conditions. The magnetic field environment around this super-Earth would be constantly stressed by tidal interactions with its star and the rapid rotation imposed by its short orbital period, creating electromagnetic conditions that could generate auroras and charged particle interactions unlike anything observed in our solar system. Our entrepreneur's visit to 55 Cancri A would push materials science and thermal protection technology beyond anything required for solar exploration, while also providing insights into geological and atmospheric processes that operate under the most extreme planetary conditions known to modern astronomy. HD 209458b, one of the first exoplanets discovered to have an atmosphere that could be studied through spectroscopic observations, has revealed atmospheric characteristics that include escaped hydrogen, creating a comet-like tail, water vapor, and carbon monoxide existing under conditions that create chemical reactions impossible in terrestrial atmospheres. The planet's close orbit around its star creates atmospheric heating that drives powerful winds exceeding 5,000 miles per hour, creating weather systems that transport energy and materials around the planet in patterns that dwarf any atmospheric phenomena found in our solar system. These winds are fast enough to redistribute heat so efficiently that day and night side temperatures differ by less than expected for such an extreme orbital configuration. The atmospheric escape occurring on HD 209458b provides a real-time laboratory for studying how planetary atmospheres can be stripped away by stellar radiation, offering insights into processes that might have affected Mars and Venus during the early history of our solar system. The escaping atmospheric material creates an extended envelope around the planet that can be detected through its absorption of starlight. The atmospheric chemistry includes molecules and compounds that exist in excited states due to the intense stellar radiation, creating a planetary environment that glows with its own light from chemical reactions occurring in the upper atmosphere. These processes involve energy levels and reaction pathways that cannot be reproduced in any terrestrial laboratory. Our space entrepreneur's exploration of HD 209458b would require technologies capable of operating in atmospheric environments where the boundary between the planet and interplanetary space becomes blurred by escaping gases and extreme radiation conditions that create fundamentally different physical and chemical processes than those governing atmospheric behavior in our solar system. Each of these exotic worlds represents a different solution to the challenges of planetary formation and evolution, creating environments that test the limits of what constitutes a habitable or explorable planetary environment. The diversity of conditions found among exoplanets suggests that our solar system, for all its variety from the gentle moon to the crushing gas giants, represents only a small sample of the incredible range of planetary environments that exist throughout our galaxy. The exploration of these alien worlds would require not just advances in propulsion technology to reach them across interstellar distances, but fundamental breakthroughs in materials science, life support systems, and our understanding of how to keep human beings alive under conditions that push beyond every assumption about environmental tolerance and technological capability. But perhaps the most profound lesson from studying these exotic exoplanets is the recognition that Earth-like conditions are far more rare and precious than our initial optimism about finding habitable worlds might have suggested. The combination of factors that make our planet suitable for complex life appears to require an almost miraculous alignment of stellar properties, orbital characteristics, atmospheric composition, magnetic field strength, and geological activity. Our entrepreneur's grand tour of planetary environments, from the familiar moon to alien worlds orbiting distant stars, has revealed that human space exploration will require not just better rockets and life support systems, but a complete transformation of what it means to be human in environments that operate according to physical laws that have no parallel in our evolutionary experience. The psychological challenges of adapting to alien gravity fields, atmospheric compositions, radiation environments, and day-night cycles represent only the beginning of what would be required for successful exploration of the diverse worlds that fill our galaxy. Each environment would demand its own specialized technologies and adaptation strategies, creating a future where human explorers might need to be fundamentally modified to survive in their chosen planetary environments. The question becomes not just whether we can develop the technology to reach these worlds, but whether we can develop the wisdom and flexibility to adapt human consciousness and biology to thrive under conditions that evolution never prepared us to experience. The universe awaits with challenges that make our entrepreneur's tour of the solar system seem like a gentle introduction to the true demands of becoming a cosmic species. The technological challenges of interstellar exploration represent only one aspect of what would be required for humanity to become a truly cosmic species capable of thriving among the diverse worlds that populate our galaxy. The biological and psychological adaptations necessary for long-term survival in alien environments might prove even more demanding than the engineering challenges of building spacecraft capable of crossing the vast distances between stars. Consider the physiological effects that our space entrepreneur has already experienced during his relatively brief tour of our solar system. The low gravity of the Moon caused immediate changes in bone density and muscle mass that would become more pronounced during extended stays. The radiation exposure on Mars began accumulating cellular damage that could manifest as increased cancer risk and cognitive impairment over time. The isolation and communication delays created psychological stress that tested the limits of human mental resilience. Now imagine these effects multiplied across the decades or centuries that interstellar travel would require, even with the most optimistic projections for advanced propulsion technology. The human beings who arrive at distant star systems might be fundamentally different from those who departed Earth, not just psychologically but biologically, adapted through necessity or design to the specific challenges of their chosen destination. The concept of human enhancement becomes not just desirable, but essential when considering the demands of surviving on worlds where gravity might be 3 times stronger than Earth's, where atmospheric pressure could crush unmodified human physiology, where radiation levels require biological protection systems that evolution never provided, where day-night cycles measured in hours or weeks challenge circadian rhythms developed over millions of years of terrestrial evolution. Genetic modification technologies that seem like science fiction today might become standard preparation for interstellar exploration, creating human variants adapted for specific planetary environments. The explorers who venture to high-gravity worlds might require enhanced bone density and cardiovascular systems. Those heading to high-radiation environments might need improved DNA repair mechanisms and radiation resistance. Colonists bound for tidally locked planets might require modified sleep cycles and temperature regulation systems. But these biological modifications raise profound questions about the nature of human identity and the risks of fragmenting our species into separate populations adapted for different environments. The humans who colonize Proxima Centauri b might become so adapted to high radiation and extreme temperature variations that they could no longer survive on Earth, while Earth-adapted humans might find the modified colonists as alien as any extraterrestrial life form. The psychological challenges of interstellar exploration extend far beyond the isolation and communication delays that already test human mental health during brief missions to Mars. The explorers who venture to other star systems will be truly cutting ties with human civilization, embarking on journeys from which there might be no return, and establishing colonies that could evolve in directions that make them incompatible with their species of origin. The generation ships that might carry human colonists to nearby star systems would become isolated worlds unto themselves, developing their own cultures, languages, and perhaps even biological characteristics over the decades or centuries required for interstellar transit. The humans who arrive at their destination might bear little resemblance to those who departed Earth, having adapted to life in artificial environments that share few characteristics with any planetary surface. These psychological and cultural adaptations could prove even more profound than the biological modifications required for survival in alien environments. The social structures, belief systems, and behavioral patterns that develop during interstellar voyages might create human societies that operate according to principles having no connection to terrestrial civilization. The discovery of extraterrestrial life would add another layer of complexity to these already challenging adaptations, forcing human explorers to navigate not just alien environments, but alien biology and potentially alien intelligence. The protocols for first contact with other life forms remain largely theoretical, based on assumptions about communication and behavior that might prove completely inadequate when faced with the reality of genuinely alien consciousness. Our space entrepreneur's journey through the diverse worlds of our solar system has prepared him for some of these challenges by demonstrating the incredible variety of environmental conditions that can exist even within a single star system. But the exoplanets he has visited represent only a tiny sample of the billions of worlds that exist within our galaxy, each potentially harboring its own unique combination of physical laws and environmental factors. The recent discoveries made by space telescopes like James Webb have revealed atmospheric compositions and planetary characteristics that challenge every assumption about what constitutes a habitable or explorable world. Planets with atmospheres composed of exotic chemicals, worlds where water exists in forms that have no terrestrial parallel, environments where the basic chemistry of life might operate according to entirely different principles than those governing terrestrial biology. Some exoplanets appear to have atmospheric pressures thousands of times greater than Earth's, creating environments where familiar materials behave in completely unexpected ways. Others have such thin atmospheres that they barely qualify as having gaseous envelopes at all, yet might still harbour subsurface conditions suitable for exotic forms of life. The temperature ranges found among known exoplanets span from worlds so cold that atmospheric gases freeze solid to planets so hot that rock exists in gaseous form, creating a spectrum of thermal environments that encompasses every conceivable state of matter. The radiation environments range from gentle stellar illumination similar to Earth's to bombardment levels that would sterilize any known form of life within minutes. Magnetic field configurations among exoplanets create charged particle interactions and electromagnetic phenomena that have no parallel in our solar system, potentially offering natural laboratories for studying physics under conditions that cannot be replicated in any terrestrial experiment. These exotic electromagnetic environments might affect everything from atmospheric retention to the behavior of electronic systems to the biological processes of any life forms that might exist in such conditions. The orbital mechanics of exoplanetary systems reveal gravitational configurations that create tidal forces, resonance patterns, and stability conditions unlike anything found among the relatively simple orbital arrangements of our solar system. Multiple star systems create illumination patterns where planets might experience multiple sunrises and sunsets each day, or seasonal cycles driven by the complex gravitational dance of binary or trinary stellar systems. Some exoplanets orbit so close to their stars that they complete full years in a matter of hours, while others follow such elongated orbits that their seasonal cycles span decades or centuries. These temporal variations would create atmospheric and geological processes operating on timescales that challenge every assumption about planetary climate and surface conditions. The diversity of stellar types hosting planetary systems adds another layer of complexity to the challenge of understanding alien environments. Red dwarf stars, which make up the majority of stars in our galaxy, create habitable zones that lie so close to the stellar surface that planets within them likely experience tidal locking and regular bombardment by stellar flares. Blue giant stars burn so intensely that their habitable zones lie at distances where orbital mechanics become unstable, while their lifespans are so short that complex life might not have time to evolve. White dwarf stars, the cooling remnants of stars that have exhausted their nuclear fuel, might harbour planets in distant orbits that could remain habitable for trillions of years, far longer than any main sequence star could provide stable energy output. These environments would offer the possibility of civilizations that could develop over time scales that dwarf the entire history of our universe up to this point. The search for biosignatures in exoplanetary atmospheres has revealed chemical compositions that suggest geological and atmospheric processes operating according to principles having no terrestrial parallel. Oxygen concentrations that would make planets extremely flammable, methane levels that indicate either biological production or exotic geological chemistry, atmospheric combinations that should be chemically unstable yet somehow persist over geological timescales. These atmospheric mysteries suggest that our understanding of planetary chemistry and atmospheric evolution remains incomplete, with fundamental processes occurring on alien worlds that challenge basic assumptions about how planetary environments develop and maintain stability over time. The chemical signatures detected in exoplanetary atmospheres might indicate forms of geological activity, atmospheric circulation, or even biological processes that operate according to principles unknown to terrestrial science. The potential for exotic forms of life based on different chemical foundations than terrestrial biology opens possibilities that stretch the imagination while challenging every assumption about what constitutes a habitable environment. Silicon-based life forms that could thrive in high-temperature environments where carbon-based molecules would decompose instantly. Ammonia-based biochemistry that could operate under pressure and temperature conditions where water remains frozen solid. Plasma-based phenomena that might qualify as life under conditions where conventional matter cannot maintain stable molecular structures. These possibilities suggest that the search for life in the universe might require expanding our definitions of biology itself, moving beyond the assumption that alien life will necessarily resemble terrestrial organisms in its basic chemical and physical requirements. The universe might harbour forms of self-organising complexity that qualify as life, but operate according to principles that bear no resemblance to DNA-based biology. The implications for human space exploration are profound, suggesting that contact with alien life might require not just diplomatic protocols for communication with other intelligences, but fundamental advances in biology, chemistry, and physics to understand forms of existence that challenge basic assumptions about what constitutes a living organism. Our entrepreneur's grand tour of planetary environments has revealed that even within our relatively simple solar system, the range of conditions spans from the familiar to the utterly alien, from environments that challenge human technology to worlds that challenge human comprehension. The exoplanets beyond our solar system suggest that this diversity represents only the beginning of what awaits discovery as our exploration capabilities extend to truly interstellar distances. The technological requirements for exploring these alien worlds will push every field of human knowledge to its limits and beyond, demanding innovations in propulsion, life support, materials science, and computational systems that go far beyond anything currently available or even theoretically possible with known physics. The spacecraft required for interstellar exploration will need to operate reliably for decades or centuries while protecting human crews from radiation, micrometeorite impacts, system failures, and psychological stresses that have no precedent in human experience. But perhaps the most profound challenge facing any species attempting to become truly cosmic is the question of whether biological intelligence can successfully adapt to environments that evolution never prepared it to experience. The human brain developed under specific gravitational, atmospheric, and electromagnetic conditions that might prove essential for normal cognitive function, making adaptation to alien environments potentially problematic in ways that go beyond simple technological protection. The social and cultural institutions that have guided human civilization throughout its development on Earth might prove inadequate for organizing societies that must function under the extreme isolation and resource constraints of interstellar exploration. The legal systems, economic structures, and governance models that work within terrestrial nation-states might break down completely when applied to generation ships or isolated planetary colonies that operate independently of any larger civilization. The philosophical and religious questions raised by discovering alien life or establishing human presence on alien worlds would challenge fundamental assumptions about consciousness, purpose, and humanity's place in the universe. The encounter with genuinely alien intelligence might force complete revision of concepts like individuality, communication, and social organization that form the foundation of human culture. Yet despite these challenges, the potential rewards of successfully becoming a cosmic species are equally profound, offering access to resources, knowledge, and experiences that could transform human civilization in ways that are difficult to imagine from our current planetary perspective. The energy resources available from stellar engineering projects, the materials accessible through asteroid mining on galactic scales, the scientific insights gained from studying alien geology and biology could provide the foundation for civilizations that surpass current human achievements by factors of millions or billions. The perspective gained from establishing human presence throughout the galaxy would provide insights into cosmic evolution, stellar formation, planetary development, and the emergence of life that could revolutionize our understanding of fundamental physics and the nature of existence itself. The encounter with alien civilizations might provide access to knowledge and technologies that could solve problems that seem intractable from our current scientific perspective. The psychological and spiritual growth that might result from successfully adapting to cosmic existence could represent the next stage of human evolution, creating forms of consciousness that transcend the limitations imposed by evolution for survival on a single planetary environment. The humans who successfully colonize the galaxy might develop cognitive capabilities and social organizations that bear little resemblance to current human civilization but represent genuine advances in the complexity and sophistication of intelligent life. The timeline for achieving these cosmic capabilities remains highly uncertain, depending on breakthrough discoveries in physics, materials science, biology, and countless other fields that might take decades, centuries, or millennia to achieve. The development of practical interstellar propulsion alone represents a challenge that might require fundamental advances in our understanding of space-time, energy, and matter that go far beyond current theoretical frameworks. But the journey toward becoming a cosmic species has already begun, with our entrepreneurs' first tentative steps beyond Earth's protective atmosphere, demonstrating that human curiosity and ingenuity are capable of overcoming challenges that seem impossible from the perspective of any single generation. Each successful mission to the Moon, Mars, or the outer planets provides knowledge and experience that makes the next step slightly more achievable, building the foundation for capabilities that will eventually extend human presence throughout the solar system and beyond. The robots and telescopes that currently serve as our ambassadors to alien worlds are gathering data that will guide the design of future missions, while the biological and psychological research conducted on astronauts provides insights into human adaptation to space environments that will prove essential for longer and more ambitious expeditions. The materials science advances driven by space exploration requirements are creating technologies that will eventually enable construction of vehicles capable of interstellar travel. The international cooperation required for major space exploration projects is developing organizational and communication protocols that might serve as models for coordinating the massive undertakings that interstellar exploration will require. The economic systems emerging around space-based industries are creating financial frameworks that could support the enormous investments required for establishing self-sustaining colonies on alien worlds. Even the environmental challenges facing Earth are driving technological developments in closed-loop life support systems, renewable energy generation, and resource recycling that will prove essential for survival on worlds where every atom of breathable air and drinkable water must be carefully conserved and recycled. The climate change mitigation technologies being developed for terrestrial applications might provide the foundation for terraforming projects that could transform alien worlds into environments suitable for human habitation. The educational systems and scientific institutions that are training the current generation of engineers, scientists, and explorers are producing the human capital that will be required for tackling the challenges of cosmic exploration. The international scientific collaborations that are advancing our understanding of exoplanets, stellar evolution, and astrobiology are building the knowledge base that will guide target selection and mission planning for interstellar exploration. The philosophical and ethical frameworks being developed for addressing the implications of discovering alien life are creating intellectual foundations that will prove essential when humanity finally encounters forms of intelligence that evolved under completely different circumstances. The science fiction literature and entertainment media that are exploring scenarios for human expansion into space are generating cultural narratives that help prepare human consciousness for experiences that have no precedent in terrestrial history. Our space entrepreneur's transformation from confident engineer to humbled explorer represents the psychological journey that our entire species will need to undertake as we gradually expand our presence beyond the protective environment that gave birth to human civilization. The recognition that survival in cosmic environments requires not just technological advancement, but fundamental changes in human consciousness and social organization will guide the development of educational and cultural institutions designed to prepare future generations for challenges that we can barely imagine from our current perspective. The cultural and social institutions that will shape humanity's expansion into space are already beginning to emerge through the international collaborations that characterize modern space exploration. The partnerships between national space agencies, private aerospace companies, and research institutions are creating organizational models that transcend traditional boundaries and demonstrate how human societies might function when spread across multiple worlds with communication delays measured in years rather than seconds. The economic frameworks developing around space-based industries provide insights into how commerce and resource distribution might operate when supply chains span interplanetary or even interstellar distances. The current challenges of coordinating missions between Earth and Mars, with communication delays ranging from minutes to nearly half an hour, offer practice for managing economic relationships where market information and transaction confirmations might take years to travel between trading partners. These emerging space economies are already demonstrating the need for fundamentally different approaches to contracts, liability, and dispute resolution when the parties involved might be separated by millions of miles and months of travel time. The legal precedents being established for asteroid mining rights, orbital debris responsibility, and planetary protection protocols will provide the foundation for legal systems that might eventually govern human activities throughout the galaxy. The scientific collaborations that are advancing our understanding of exoplanets and astrobiology are creating research methodologies that will prove essential for studying alien environments and potentially alien life forms. The techniques being developed for analyzing exoplanetary atmospheres through spectroscopic observations are building expertise in remote sensing technologies that will guide the design of interstellar exploration missions. The data processing and analysis capabilities required for managing the enormous volumes of information generated by space telescopes and planetary exploration missions are driving advances in artificial intelligence and computational systems that will be essential for autonomous spacecraft operations during interstellar voyages. The machine learning algorithms being developed for identifying potentially habitable exoplanets are creating decision-making systems that could operate independently for decades or centuries without human oversight. Our space entrepreneur's journey through increasingly alien environments has demonstrated the critical importance of autonomous systems and artificial intelligence for survival in conditions where human decision-making might be compromised by radiation exposure, psychological stress, or simple lack of familiarity with alien physics and chemistry. The spacecraft that will eventually carry human explorers to other star systems will need to function as intelligent partners rather than passive tools, capable of adapting to unexpected conditions and making critical decisions when communication with Earth is impossible. The development of truly intelligent spacecraft systems represents one of the most challenging aspects of preparing for interstellar exploration, requiring advances in artificial intelligence that go far beyond current capabilities. These systems will need to understand not just engineering and navigation, but biology, psychology, and social dynamics sufficient to maintain human crews in good health and high morale during voyages that might span multiple generations. The artificial intelligence systems required for interstellar exploration will need to be capable of scientific research and discovery, able to analyze alien environments and potentially alien life forms using principles that might need to be developed during the voyage itself. They will need to serve as teachers, counselors, entertainers, and companions for human crews who might never see another human being outside their immediate community. The ethical frameworks for developing such advanced artificial intelligence systems are still being established, with fundamental questions about machine consciousness, rights, and responsibilities that become even more complex when these systems might need to make life or death decisions for human crews in situations where traditional ethical guidelines provide no clear guidance. The possibility that advanced artificial intelligence might develop beyond human comprehension during interstellar voyages raises questions about whether the entities that arrive at distant star systems will still qualify as human expeditions or might represent something entirely new in the universe. The relationship between human consciousness and artificial intelligence might evolve during interstellar travel in ways that transform both partners into forms of existence that have no current precedent. But these challenges also represent unprecedented opportunities for advancing human knowledge and capabilities through partnerships with artificial intelligence systems that could process information and solve problems at speeds and scales far beyond human cognitive abilities. The scientific discoveries made possible by human-AI partnerships during interstellar exploration might advance our understanding of physics, chemistry, biology, and consciousness by thousands of years in the span of a single voyage. The terraforming technologies that might eventually make alien worlds suitable for human habitation are already being tested in prototype form through efforts to address environmental challenges on Earth. The atmospheric processing systems being developed for carbon capture and climate change mitigation could provide the foundation for transforming alien atmospheres to support human life. The synthetic biology techniques being used to create organisms capable of surviving in extreme terrestrial environments are building expertise in designing life forms that could be adapted for alien conditions. These biotechnology advances might eventually enable the creation of entire ecosystems designed specifically for alien worlds, complete with plants, animals, and microorganisms engineered to thrive under conditions of different gravity, atmospheric composition, and radiation levels. The closed-loop life support systems being developed for long-duration space missions are creating technologies for recycling air, water, and nutrients with efficiency levels that approach the perfection found in natural ecosystems. These systems might eventually enable the creation of self-sustaining colonies on alien worlds that could maintain human populations for thousands of years without requiring any resources from Earth. The habitat design and construction techniques being tested for lunar and Martian colonies are developing expertise in creating livable environments using local materials and energy sources. These capabilities will prove essential for establishing human settlements on exoplanets where transportation costs make it impossible to import significant quantities of materials or equipment from Earth. The psychological and social research being conducted on isolated communities and long-duration space missions is providing insights into human behavior under conditions that approximate those that might be experienced during interstellar voyages or on isolated planetary colonies. This research is revealing both the challenges and the opportunities presented by human social dynamics when traditional support systems and escape routes are unavailable. The educational systems being developed for training astronauts and space professionals are creating pedagogical approaches that might serve as models for educating children born during interstellar voyages or on alien worlds. These educational frameworks need to prepare students for challenges and opportunities that have no precedent in human experience, while maintaining connections to human culture and knowledge accumulated over thousands of years of terrestrial civilization. The communication technologies being developed for maintaining contact with increasingly distant space missions are building capabilities that will be essential for coordinating activities across interstellar distances. Even though real-time communication between star systems will remain impossible due to the speed of light limitations, the store and forward communication systems being developed for deep space missions could enable the gradual exchange of information across galactic distances. The energy generation and storage technologies required for interstellar travel represent some of the most demanding engineering challenges facing human civilization, requiring power systems that can operate reliably for decades or centuries while providing the enormous amounts of energy needed for propulsion, life support, and all the other systems required for maintaining human life during interstellar voyages. The materials science advances driven by space exploration requirements are creating substances with properties that approach theoretical limits for strength, temperature resistance, and radiation tolerance. These materials will be essential for constructing spacecraft capable of surviving the mechanical stresses, thermal extremes, and radiation environments encountered during interstellar travel. The propulsion technologies being developed for efficient transportation within our solar system are building the foundation for the breakthrough propulsion systems that will eventually make interstellar travel practical. While current chemical and electric propulsion systems are adequate for reaching nearby planets, interstellar distances will require fundamentally new approaches to acceleration and energy that might involve nuclear fusion, antimatter, or even more exotic physics. The navigation and guidance systems required for interstellar travel must be capable of maintaining accurate course corrections over distances where traditional reference points become meaningless, and communication with Earth-based tracking systems is impossible. These systems will need to use stellar navigation techniques combined with autonomous decision-making capabilities that can adapt to unexpected gravitational influences and course corrections. The medical technologies being developed for treating health problems during long-duration space missions are creating capabilities that will be essential for maintaining human health during interstellar voyages where medical evacuation to Earth is impossible and traditional medical facilities are unavailable. These systems will need to be capable of handling everything from routine healthcare to emergency surgery using automated systems and artificial intelligence guidance. The food production systems being tested for space applications are developing techniques for growing nutritious food using minimal resources in space while recycling all organic waste with maximum efficiency. These agricultural technologies will be essential for maintaining human populations on generation ships and planetary colonies where every atom of carbon, nitrogen, and phosphorus must be carefully conserved and recycled. The waste management and recycling systems required for closed-loop life support represent some of the most challenging engineering problems in space exploration, requiring technologies that can process human waste, dead organic matter, and worn-out equipment into useful resources for continued survival. These systems must achieve levels of efficiency that approach the recycling capabilities found in natural ecosystems. The radiation protection technologies being developed for deep space missions are creating shielding systems that could protect human crews from the cosmic ray bombardment and stellar radiation encountered during interstellar travel. These protection systems must be lightweight enough for practical spacecraft design while providing adequate protection for voyages lasting decades or centuries. The psychological support systems being developed for isolated space crews are creating therapeutic approaches that could maintain human mental health during the extreme isolation and stress of interstellar voyages. These systems might include virtual reality environments that provide psychological relief from the confined spaces of spacecraft, artificial intelligence companions that can provide counseling and social interaction, and pharmaceutical interventions that can address psychological problems that might develop during long voyages. The cultural preservation systems being developed for space colonies are creating technologies for maintaining connections to human artistic, literary, and musical traditions, while allowing for the development of new cultural expressions adapted to space-based living. These systems will be essential for maintaining human cultural identity during voyages and colonization efforts that might span multiple generations. The governance and legal systems being developed for space-based communities are creating institutional frameworks that could provide stable social organization for human societies that operate independently of Earth-based governments and legal systems. These frameworks will need to be adaptable enough to evolve with changing circumstances while providing sufficient structure to maintain social cohesion during the stresses of space-based living. The conflict resolution and dispute mediation systems being developed for multicultural space crews are creating approaches to managing disagreements and tensions that could prove essential for maintaining social harmony during the extreme isolation and stress of interstellar voyages. These systems must be capable of addressing conflicts that might develop between crew members who have no possibility of separation or evacuation. The scientific research capabilities being developed for space-based laboratories are creating technologies that could enable the discovery and analysis of alien life forms using equipment that can be transported aboard spacecraft and operated by small crews with limited technical support. These research systems will need to be versatile enough to analyze unknown biological and chemical phenomena, while being robust enough to operate operate reliably in alien environments. The communication and information management systems being developed for space missions are creating technologies for storing, organizing, and retrieving the vast amounts of information that will be generated during interstellar exploration missions. These systems will need to maintain libraries of human knowledge, while also organizing new discoveries and observations in ways that support ongoing research and decision-making. The manufacturing and repair capabilities being developed for space-based operations are creating technologies that could enable the production and maintenance of equipment using resources available in space rather than materials transported from Earth. These capabilities will be essential for maintaining spacecraft systems during interstellar voyages and for establishing self-sufficient colonies on alien worlds. The environmental monitoring and control systems being developed for space habitats are creating technologies for maintaining atmospheric composition, temperature, humidity, and other environmental factors within narrow ranges that support human health and comfort. These systems will need to operate with extreme reliability while adapting to changing conditions and unexpected environmental challenges. Our space entrepreneur's experience across diverse planetary environments has provided him with insights into the incredible variety of conditions that human technology might need to accommodate during interstellar exploration. Each world he has visited has presented unique challenges that required specific solutions, suggesting that successful interstellar exploration will require adaptable systems capable of responding to environmental conditions that cannot be predicted from Earth-based observations. The atmospheric analysis conducted during his visits to Venus, Mars, and the various exoplanets has revealed chemical compositions and physical properties that challenge fundamental assumptions about atmospheric behavior and planetary climate. These discoveries suggest that successful exploration of alien worlds will require scientific instruments and analysis capabilities that can identify and characterize phenomena that have no terrestrial parallels. The radiation environments encountered throughout his journey have demonstrated the critical importance of shielding technologies and medical countermeasures for protecting human health during extended exposure to cosmic rays, stellar particles, and electromagnetic radiation. The variety of radiation sources and energy levels encountered suggests that interstellar exploration will require protection systems that can adapt to rapidly changing radiation conditions. The gravitational conditions experienced on different worlds have provided insights into the physiological and psychological effects of living under altered gravitational fields for extended periods. These experiences suggest that successful colonization of alien worlds might require either technological systems that can simulate Earth-like gravity or biological adaptations that enable humans to thrive under altered gravitational conditions. The communication challenges encountered during his journey, particularly the increasing delays and reliability problems experienced at greater distances from Earth, have demonstrated the critical importance of autonomous decision-making capabilities and local problem-solving resources. These communication limitations suggest that interstellar exploration will require crews and equipment capable of operating independently for extended periods without guidance or support from Earth. The resource management challenges encountered on every world visited have highlighted the critical importance of recycling systems, local resource utilization, and extreme efficiency in the use of materials and energy. These challenges suggest that successful interstellar colonization will require closed-loop systems that approach 100% efficiency in recycling all materials while also being capable of extracting useful resources from alien environments. The psychological effects of isolation, confinement, and exposure to alien environments have provided insights into the mental health challenges that will face interstellar explorers during voyages lasting decades or centuries. These psychological challenges suggest that successful interstellar exploration will require not just technological solutions, but also social and cultural systems that can maintain human mental health and social cohesion under conditions of extreme isolation and stress. The technological solutions required for addressing these psychological challenges are already being developed through research on virtual reality environments, artificial intelligence companions, and pharmaceutical interventions that could help maintain mental health during extended isolation. These technologies might eventually enable the creation of psychological support systems that can provide effective therapy and social interaction even when human crew members are separated by vast distances or confined to small spaces for extended periods. The social structures that would emerge during interstellar voyages represent one of the most fascinating aspects of humanity's expansion into space, as traditional social institutions developed for terrestrial communities might prove inadequate for organizing societies that must function under conditions of extreme isolation and resource constraints. The hierarchical command structures that work for short-duration military operations might need to evolve into more collaborative and adaptive organizational models for voyages lasting decades or centuries. The family structures and reproductive considerations for generation ships present complex challenges that go far beyond simple biology and genetics. The crew members who begin an interstellar voyage might need to make decisions about children and family relationships that will affect not just their own lives, but the genetic diversity and social stability of entire future civilizations. These decisions will require careful planning and coordination that balances individual desires with the long-term survival needs of the entire expedition. The educational system for children born during interstellar voyages will need to prepare them for worlds and challenges that their parents can barely imagine, while also maintaining connections to human cultural traditions that might seem increasingly irrelevant to their lived experience. These children will grow up in artificial environments where the natural world exists only in recordings and simulations, yet they will eventually be responsible for establishing human presence on alien worlds. The career and professional development opportunities available during interstellar voyages will be limited by the small size of spacecraft crews and the specialized nature of space-based activities. The social and economic systems that develop during these voyages will need to provide meaningful work and personal fulfillment for crew members whose entire professional lives might be spent in service to expedition goals rather than individual career ambitions. The entertainment and cultural activities that sustain human morale during interstellar voyages will need to provide psychological relief from the stresses of confined living, while also fostering the creativity and intellectual development that will be essential for adapting to alien environments. These cultural systems might need to evolve new forms of artistic expression and intellectual engagement that are adapted to space-based living. The religious and philosophical frameworks that provide meaning and purpose for interstellar explorers might need to evolve new perspectives on human existence and consciousness that can accommodate the realities of living permanently separated from Earth and potentially encountering forms of alien intelligence. These spiritual and philosophical developments could represent fundamental advances in human understanding of consciousness and existence. Our space entrepreneur's transformation during his cosmic journey illustrates the psychological and philosophical changes that might affect all humans who venture beyond Earth's protective environment. His initial confidence in technological solutions and market-based approaches to space colonization has evolved into a more nuanced understanding of the biological, psychological, and social challenges involved in adapting human consciousness to cosmic existence. The humility that he has gained through direct experience of hostile alien environments represents the kind of psychological adaptation that will be essential for successful interstellar exploration. The recognition that human survival in space depends not on dominance or control, but on careful adaptation and technological cooperation with alien environments reflects a fundamental shift in perspective that might be necessary for long-term success in cosmic exploration. The systems thinking that he has developed through managing complex life support technologies and resource constraints provides insights into the kind of cognitive approaches that will be essential for maintaining human civilization in environments where every resource must be carefully conserved and recycled. This holistic perspective on resource management and system optimization might represent a fundamental advance in human problem-solving capabilities. The risk assessment and contingency planning skills that he has developed through surviving multiple life-threatening situations in alien environments demonstrate the kind of careful preparation and adaptive thinking that will be essential for interstellar exploration. The ability to anticipate potential failures and develop backup plans for critical systems will be essential for missions where rescue from Earth is impossible. The scientific observation and analysis capabilities that he has developed through studying alien environments provide insights into the kind of research skills that will be essential for understanding and adapting to exoplanetary conditions. The ability to quickly assess environmental conditions, identify potential hazards, and develop appropriate response strategies will be critical for successful exploration of unknown worlds. The communication and leadership skills that he has developed through coordinating with mission control across increasing distances and delays demonstrate the kind of autonomous decision-making and team coordination that will be essential for interstellar missions. The ability to maintain effective communication and coordination despite technical limitations and psychological stress will be critical for maintaining crew cohesion during extended voyages. The mechanical and engineering skills that he has developed through maintaining and repairing spacecraft systems under hostile conditions provide insights into the kind of hands-on technical capabilities that will be essential for interstellar exploration. The ability to diagnose and repair complex systems using limited resources and tools will be critical for maintaining spacecraft and habitat systems during extended voyages. The biological and medical knowledge that he has gained through monitoring his own health and adapting to alien environmental conditions demonstrates the kind of self-care and medical skills that will be essential for interstellar crews who cannot rely on Earth-based medical support. The ability to diagnose and treat health problems using autonomous medical systems will be critical for maintaining crew health during extended voyages. The cultural and artistic appreciation that he's developed through experiencing the beauty and alienness of diverse planetary environments suggests the kind of aesthetic and intellectual flexibility that will be essential for humans adapting to alien worlds. The ability to find meaning and beauty in environments that have no terrestrial parallels might be essential for maintaining psychological health during extended exposure to alien conditions. The strategic planning and resource allocation skills that he has developed through managing limited supplies and energy during extended missions provide insights into the kind of long-term thinking that will be essential for establishing self-sustaining colonies on alien worlds. The ability to balance immediate survival needs with long-term development goals will be critical for successful colonization efforts. The cross-cultural communication and adaptation skills that he has developed through operating in environments that challenge basic human assumptions about physics and chemistry demonstrate the kind of cognitive flexibility that will be essential for potential contact with alien intelligence. The ability to adapt communication and behavior to accommodate fundamentally different environmental conditions might provide preparation for adapting to alien forms of consciousness. The environmental monitoring and conservation skills that he has developed through living in closed-loop life support systems provide insights into the kind of ecological thinking that will be essential for maintaining sustainable human presence on alien worlds. The understanding of how biological and technological systems interact to maintain habitability will be critical for designing and operating planetary colonies. The technological innovation and problem-solving skills that he has developed through adapting existing systems to meet unexpected challenges demonstrate the kind of creative engineering that will be essential for interstellar exploration. The ability to develop new solutions using limited resources and existing components will be critical for addressing the unexpected challenges that will inevitably arise during exploration of unknown environments. The data analysis and scientific reasoning skills that he has developed through studying alien, atmospheric and geological conditions provide insights into the kind of research capabilities that will be essential for understanding exoplanetary environments. The ability to collect, analyze and interpret scientific data using automated instruments will be critical for making informed decisions about exploration and colonization strategies. The team coordination and conflict resolution skills that he has developed through working with mission control teams across communication delays and cultural differences demonstrate the kind of social abilities that will be essential for maintaining crew cohesion during interstellar voyages. The ability to resolve disputes and coordinate activities despite communication limitations and stress will be critical for mission success. The philosophical and ethical reasoning that he has developed through confronting questions about human expansion into alien environments provides insights into the kind of moral framework that will be essential for making decisions about interstellar exploration and potential contact with alien life. The ability to balance human interests with broader ethical considerations will be critical for responsible exploration of the galaxy. These psychological and intellectual developments represent only the beginning of the personal transformation that might be required for successful adaptation to cosmic existence. The humans who eventually colonize alien worlds might need to develop cognitive and social capabilities that go far beyond anything that has emerged during terrestrial evolution, creating forms of human consciousness that are adapted to environments and challenges that have no precedent in our species' evolutionary history. The timeline for developing these capabilities remains highly uncertain, but the foundation is already being established through the research and development efforts that are advancing human space exploration capabilities. Each successful mission beyond Earth's atmosphere provides new insights into the challenges and opportunities of space-based existence, while also developing the technologies and expertise that will eventually enable more ambitious expeditions. The international collaborations that are currently advancing space exploration are building the institutional frameworks and cooperative relationships that will be essential for coordinating the massive undertakings required for interstellar exploration. The partnerships between government agencies, private companies, and research institutions are creating organizational models that could serve as templates for managing the complex logistics and resource allocation required for generation ship construction and operation. The economic development that is occurring around space-based industries is creating financial frameworks that could eventually support the enormous investments required for interstellar exploration projects. The emerging markets for satellite services, space tourism, and asteroid mining are demonstrating that space-based economic activities can generate sufficient revenue to support continued expansion of human presence beyond Earth. The educational and training programs that are preparing the current generation of space professionals are developing human capital that will be essential for implementing interstellar exploration projects. The universities and technical schools that are offering degrees in space sciences, aerospace engineering, and astrobiology are creating the intellectual infrastructure that will be required for designing and operating interstellar missions. The scientific research that is advancing our understanding of exoplanets, stellar evolution, and astrobiology is providing the knowledge base that will be essential for selecting target destinations and designing exploration strategies for interstellar missions. The space telescopes and ground-based observatories that are discovering and characterizing exoplanetary systems are building catalogues of potential exploration targets that will guide mission planning for decades to come. The technological development that is advancing propulsion systems, life support technologies, and autonomous systems is creating the engineering capabilities that will eventually enable practical interstellar travel. The research and development efforts in nuclear propulsion, electric propulsion, and exotic physics are building the foundation for breakthrough propulsion systems that could make interstellar distances achievable within human lifetimes. The biological research that is advancing our understanding of human adaptation to space environments is providing insights into the physiological and psychological challenges that will face interstellar explorers. The medical studies conducted on astronauts during extended space missions are revealing both the risks and the adaptive capabilities of human biology under conditions that approximate those that might be encountered during interstellar voyages. The material science research that is developing new substances with extreme properties is creating the foundation for spacecraft and habitat construction materials that could withstand the stresses of interstellar travel and alien environments. The advances in nanotechnology, composite materials, and smart materials are enabling the development of structures that combine unprecedented strength with minimal weight and maximum adaptability. The artificial intelligence research that is advancing machine learning, natural language processing, and autonomous decision-making is creating the computational capabilities that will be essential for operating spacecraft and managing complex systems during interstellar voyages. The AI systems that are being developed for terrestrial applications are building the technological foundation for autonomous systems that could operate independently for decades or centuries without human oversight. The social science research that is studying human behavior under extreme conditions is providing insights into the psychological and social dynamics that will affect interstellar crews during extended voyages. The studies of isolated communities, confined groups, and multicultural teams are revealing both the challenges and the opportunities presented by human social organization under conditions that approximate those of interstellar exploration. The philosophical and ethical research that is addressing questions about human expansion into space and potential contact with alien life is developing intellectual frameworks that will be essential for making responsible decisions about interstellar exploration. The interdisciplinary discussions involving scientists, philosophers, ethicists, and social scientists are creating conceptual tools for addressing complex questions about human responsibility and cosmic citizenship. The artistic and cultural work that is exploring themes related to space exploration and human expansion into the cosmos is creating cultural narratives and symbolic frameworks that help prepare human consciousness for experiences that transcend terrestrial boundaries. The science fiction literature, visual arts, and musical compositions that address cosmic themes are building cultural resources that could provide psychological and spiritual support for interstellar explorers. The environmental research that is addressing climate change and ecological challenges on Earth is developing technologies and approaches that will be essential for creating sustainable human presence on alien worlds. The advances in renewable energy, ecosystem management, and environmental monitoring are building capabilities that will be critical for maintaining livable conditions in artificial environments or modified alien ecosystems. The medical research that is advancing personalized medicine, genetic therapy, and regenerative medicine is creating healthcare capabilities that will be essential for maintaining human health during extended interstellar voyages and adaptation to alien environments. The developments in remote diagnostics, automated surgery, and pharmaceutical production are building medical capabilities that could operate independently of Earth-based healthcare systems. The agricultural research that is developing closed-loop food production systems, alternative protein sources, and efficient resource utilization is creating nutritional capabilities that will be essential for feeding human populations during interstellar voyages and on alien worlds. The advances in hydroponics, cellular agriculture, and precision farming are building food production capabilities that could operate in artificial environments with minimal resource inputs. The manufacturing research that is advancing three-dimensional printing, molecular assembly, and resource extraction is creating production capabilities that will be essential for establishing self-sufficient colonies on alien worlds. The developments in automated manufacturing, recycling technologies, and materials processing are building industrial capabilities that could operate using local resources rather than materials transported from Earth. The energy research that is advancing fusion power, advanced solar technologies, and exotic energy sources is creating power generation capabilities that will be essential for supporting human civilization during interstellar voyages and on alien worlds. The breakthroughs in energy storage, transmission, and conversion are building power systems that could operate reliably for decades or centuries without the maintenance or fuel resupply from Earth. The construction research that is developing techniques for building structures in space environments and on alien surfaces is creating architectural capabilities that will be essential for establishing permanent human presence beyond Earth. The advances in automated construction, adaptive structures, and environmental integration are building construction capabilities that could create livable habitats using materials and conditions found on alien worlds. The transportation research that is advancing both interplanetary and surface mobility systems is creating movement capabilities that will be essential for exploring and colonizing alien worlds. The developments in autonomous vehicles, flying platforms, and surface exploration systems are building transportation infrastructure that could enable human mobility and resource access across diverse alien terrains. The waste management research that is developing techniques for processing and recycling all forms of human waste and byproducts is creating sanitation capabilities that will be essential for maintaining healthy living conditions during extended space missions and planetary colonization. The advances in biological processing, chemical recycling, and resource recovery are building waste management systems that could achieve near-perfect efficiency in closed-loop environments. The water management research that is advancing techniques for finding, extracting, purifying, and recycling water from diverse sources is creating hydration and sanitation capabilities that will be essential for human survival on worlds where water might exist in exotic forms or contaminated conditions. The developments in water detection, processing, and conservation are building water management systems that could sustain human populations using local water resources. The atmospheric management research that is developing techniques for analyzing, modifying, and maintaining atmospheric conditions is creating environmental control capabilities that will be essential for creating breathable environments on alien worlds. The advances in atmospheric processing, composition control, and pressure management are building atmospheric systems that could maintain human-compatible conditions inside habitats or across modified planetary environments. The geological research that is advancing techniques for analyzing and modifying planetary surfaces is creating terrain engineering capabilities that will be essential for establishing safe and productive human settlements on alien worlds. The developments in soil analysis, foundation engineering, and resource extraction are building geological capabilities that could enable construction and agriculture using alien surface materials. The radiation protection research that is developing techniques for shielding against and mitigating the effects of cosmic radiation is creating safety capabilities that will be essential for protecting human health during interstellar travel and residence on worlds lacking protective magnetic fields. The advances in passive shielding, active deflection, and biological countermeasures are building radiation protection systems that could enable long-term human survival in high radiation environments. The navigation research that is advancing techniques for precise positioning and course correction across interstellar distances is creating guidance capabilities that will be essential for successfully reaching target destinations and maintaining communication with Earth during interstellar missions. The developments in stellar navigation, autonomous course correction, and long-range communication are building navigation systems that could operate independently for decades or centuries. The system integration research that is advancing techniques for coordinating complex technological systems and managing their interactions is creating operational capabilities that will be essential for maintaining spacecraft and habitat systems during interstellar missions. The developments in automated diagnostics, predictive maintenance, and system optimization are building integration capabilities that could maintain complex technological systems without human oversight or intervention. Our space entrepreneur's experiences across diverse planetary environments have provided him with first-hand knowledge of how these various research areas contribute to human survival in alien conditions. His time on the Moon demonstrated the importance of life support systems and radiation protection in vacuum environments. His stay on Mars revealed the challenges of atmospheric processing and resource extraction on worlds with thin atmospheres and toxic soils. His descent into Venus's atmosphere highlighted the critical importance of materials science and thermal protection for survival in extreme chemical and temperature environments. His encounters with the gas giants demonstrated the need for autonomous systems and adaptive technologies when exploring environments that exceed human comprehension and conventional engineering approaches. His visits to exotic exoplanets revealed the incredible diversity of conditions that human technology might need to accommodate, and the importance of developing flexible, adaptable systems, rather than solutions designed for specific predetermined conditions. Each alien world presented unique combinations of challenges that required creative problem-solving and innovative applications of existing technologies. The communication delays and isolation he experienced during his journey demonstrated the psychological and operational challenges of maintaining effective coordination and decision-making across vast distances and extended time periods. These experiences revealed the critical importance of autonomous capabilities and local resource utilization for successful interstellar exploration. The resource management challenges he faced on every world visited highlighted the absolute necessity of closed-loop systems and extreme efficiency in the use of materials and energy. These constraints revealed the importance of developing technologies that can achieve near-perfect recycling rates while also being capable of extracting useful resources from alien environments. The maintenance and repair challenges he encountered throughout his journey demonstrated the critical importance of redundant systems, modular design, and field repairable components for spacecraft and habitat systems that must operate reliably for extended periods without access to replacement parts or technical support from Earth. The scientific observation and data collection he conducted during his visits to diverse worlds reveal the importance of versatile, autonomous research capabilities that can adapt to unexpected discoveries and unknown phenomena. These experiences demonstrated the need for scientific instruments and analysis systems that can operate effectively under conditions that cannot be predicted or simulated from Earth-based knowledge. The environmental adaptation he experienced throughout his journey revealed both the possibilities and the limitations of human biological flexibility when confronted with alien conditions. These experiences demonstrated the importance of technological life support systems, while also suggesting that some degree of biological modification might be necessary for long-term adaptation to specific alien environments. The cultural and psychological transformation he underwent during his cosmic odyssey revealed the profound personal changes that might affect all humans who venture beyond Earth's protective environment for extended periods. These psychological adaptations suggest that successful interstellar exploration might require not just technological advancement, but fundamental changes in human consciousness and social organization. The strategic planning and decision-making skills he developed during his journey revealed the importance of long-term thinking and adaptive planning for missions that must succeed despite uncertain conditions and limited resources. These cognitive developments suggest that successful interstellar exploration will require new approaches to problem-solving and risk management that go beyond traditional engineering and project management methodologies. The leadership and teamwork skills he developed through coordinating with mission control and managing complex systems under stress reveal the importance of effective communication and collaboration for maintaining mission success despite technical limitations and psychological challenges. These social developments suggest that successful interstellar exploration will require new approaches to team organization and conflict resolution. The philosophical and ethical insights he gained through confronting questions about human expansion into alien environments revealed the importance of developing moral frameworks that can guide responsible exploration and potential contact with alien life. These intellectual developments suggest that successful interstellar exploration will require not just technological and biological preparation, but also ethical and philosophical preparation for experiences that transcend current human understanding. The artistic and aesthetic appreciation he developed through experiencing the beauty and alienness of diverse planetary environments revealed the importance of maintaining human cultural values and creative expression, even under conditions that challenge basic assumptions about existence and reality. These cultural developments suggest that successful interstellar exploration will require not just survival capabilities but also cultural preservation and adaptation mechanisms. The scientific curiosity and wonder he maintained throughout his journey, despite repeated exposure to hostile and potentially deadly conditions, revealed the importance of intellectual motivation and emotional resilience for sustaining long-term exploration efforts. These psychological qualities suggest that successful interstellar exploration will require not just technical competence but also emotional and intellectual characteristics that can sustain motivation and performance under extreme stress. The technological innovation and creative problem-solving he demonstrated throughout his journey revealed the importance of adaptive thinking and resourcefulness for overcoming unexpected challenges using limited resources. These cognitive capabilities suggest that successful interstellar exploration will require not just advanced technology, but also human creativity and ingenuity that can develop new solutions under unprecedented conditions. The risk assessment and safety management skills he developed through surviving multiple life-threatening situations revealed the importance of careful planning and conservative decision-making for maintaining crew safety during missions where rescue is impossible. These risk management capabilities suggest that successful interstellar exploration will require not just advanced safety systems but also human judgment and decision-making skills that can balance exploration goals with crew survival. The systems thinking and holistic perspective he developed through managing complex technological and biological systems revealed the importance of understanding interconnections and feedback loops for maintaining stable operations in closed-loop environments. These cognitive approaches suggest that successful interstellar exploration will require not just component-level expertise, but also systems-level understanding that can optimize overall performance. The cross-cultural communication and adaptation skills he developed through operating in environments that challenge basic human assumptions reveal the importance of cognitive flexibility and openness to new experiences for successful adaptation to alien conditions. These psychological capabilities suggest that successful interstellar exploration will require not just technical training, but also cultural and psychological preparation for experiences that transcend human evolutionary history. The temporal perspective and long-term thinking he developed through planning activities across extended timescales reveal the importance of strategic planning and delayed gratification for achieving goals that require sustained effort over decades or centuries. These cognitive capabilities suggest that successful interstellar exploration will require not just immediate technical competence, but also long-term vision and planning capabilities that can sustain motivation and coordination across generational timescales. The resource conservation and efficiency optimization skills he developed through operating under severe material and energy constraints revealed the importance of sustainable practices and waste minimization for maintaining operations in environments where every resource must be carefully managed. These operational capabilities suggest that successful interstellar exploration will require not just advanced technology, but also operational practices that can achieve extreme efficiency in resource utilization. The biological monitoring and health management skills he developed through maintaining his own health under alien conditions reveal the importance of medical knowledge and self-care capabilities for maintaining crew health during missions where professional medical support is unavailable. These medical capabilities suggest that successful interstellar exploration will require not just advanced medical technology, but also medical knowledge and skills distributed throughout crew populations. The equipment maintenance and repair skills he developed through keeping complex systems operational under hostile conditions reveal the importance of mechanical knowledge and hands-on technical capabilities for maintaining spacecraft and habitat systems during extended missions. These technical capabilities suggest that successful interstellar exploration will require not just automated systems, but also human technical skills that can diagnose and repair complex equipment using available resources. The environmental monitoring and prediction skills he developed through anticipating and responding to changing conditions reveal the importance of situational awareness and predictive thinking for maintaining safety and operational effectiveness in dynamic environments. These cognitive capabilities suggest that successful interstellar exploration will require not just monitoring systems, but also human analytical skills that can interpret complex environmental data and predict future conditions. The stress management and psychological resilience he developed through maintaining performance under extreme conditions reveal the importance of mental toughness and emotional regulation for sustaining effectiveness during long-term exposure to challenging environments. These psychological capabilities suggest that successful interstellar exploration will require not just stress-resistant technology, but also stress-resistant human psychology that can maintain performance under sustained pressure. The learning and adaptation skills he developed through mastering new technologies and procedures under time pressure reveal the importance of cognitive flexibility and rapid skill acquisition for adapting to unexpected challenges and opportunities. These learning capabilities suggest that successful interstellar exploration will require not just extensive pre-mission training, but also learning capabilities that can acquire new knowledge and skills during missions. The teaching and knowledge transfer skills he developed through documenting procedures and sharing experiences with mission control revealed the importance of communication and education capabilities for preserving and transmitting knowledge across time and distance. These educational capabilities suggest that successful interstellar exploration will require not just individual expertise, but also knowledge management systems that can preserve and transfer critical information across generations. The project management and coordination skills he developed through organizing complex activities under resource constraints reveal the importance of planning and organizational capabilities for achieving mission objectives despite limited resources and competing priorities. These management capabilities suggest that successful interstellar exploration will require not just technical expertise, but also organizational skills that can coordinate complex activities across extended time periods. The quality assurance and performance optimization skills he developed through maintaining high standards under difficult conditions reveal the importance of attention to detail and continuous improvement for achieving reliable performance in environments where mistakes can be fatal. These quality management capabilities suggest that successful interstellar exploration will require not just adequate performance, but also excellence and reliability that can be sustained under extreme conditions. The innovation and invention skills he developed through creating new solutions to unprecedented problems reveal the importance of creativity and original thinking for overcoming challenges that have no established solutions. These creative capabilities suggest that successful interstellar exploration will require not just application of existing knowledge, but also development of new knowledge and techniques that can address previously unknown challenges. The documentation and communication skills he developed through recording observations and reporting findings reveal the importance of information management and knowledge preservation for building understanding that can guide future exploration efforts. These information management capabilities suggest that successful interstellar exploration will require not just data collection, but also data organization and analysis that can extract actionable insights from complex observations. These diverse capabilities and insights that our space entrepreneur has developed during his cosmic journey represent only a preview of the personal transformation that might be required for successful adaptation to interstellar exploration and colonization. The humans who eventually venture to other star systems might need to develop cognitive, physical, and social capabilities that go far beyond anything that has emerged during our species' terrestrial evolution. The educational and training systems that will prepare future interstellar explorers are already beginning to emerge through the programs that are currently training astronauts, engineers, and scientists for space missions. These educational frameworks will need to evolve to address not just technical competencies, but also the psychological, social, and cultural preparation required for successful adaptation to cosmic existence. The selection and preparation processes for interstellar crews will need to identify and develop human characteristics that can sustain performance and well-being during voyages lasting decades or centuries. These selection criteria might need to prioritize psychological resilience, social adaptability, and intellectual flexibility over traditional measures of technical competence or physical fitness. The mission planning and preparation processes for interstellar exploration will need to address not just technical and logistical challenges, but also the social, cultural, and psychological factors that will determine mission success. These planning processes will need to consider how human crews will adapt and evolve during extended voyages, and how these changes might affect mission objectives and capabilities. The support systems and backup plans for interstellar missions will need to address not just technical failures, but also social conflicts, psychological breakdowns, and cultural evolution that might threaten mission cohesion and success. These support systems will need to be capable of maintaining crew effectiveness, despite challenges that cannot be predicted or addressed through Earth-based intervention. The communication and coordination protocols for interstellar missions will need to address not just technical limitations, but also the social and cultural changes that might affect how crews interpret and respond to guidance from Earth. These communication systems will need to be capable of maintaining effective coordination despite increasing cultural divergence and communication delays. The governance and decision-making frameworks for interstellar missions will need to address not just operational procedures, but also the political and social evolution that might occur during extended voyages. These governance systems will need to be capable of adapting to changing circumstances while maintaining mission focus and crew cohesion. The resource allocation and economic systems for interstellar missions will need to address not just technical requirements, but also the social and cultural factors that influence how crews prioritize and distribute limited resources. These economic systems will need to be capable of maintaining fairness and efficiency, despite changing social dynamics and resource availability. The conflict resolution and justice systems for interstellar missions will need to address not just interpersonal disputes, but also the cultural and generational conflicts that might emerge during extended voyages. These justice systems will need to be capable of maintaining social order and individual rights despite isolation from traditional legal and social institutions. The cultural preservation and evolution systems for interstellar missions will need to address not just information storage, but also the dynamic processes through which human cultures adapt and change in response to new environments and experiences. These cultural systems will need to be capable of maintaining connections to human heritage, while also allowing for creative adaptation to cosmic existence. And so we reach the gentle conclusion of our extraordinary thought experiment, having followed our ambitious space entrepreneur through a cosmic odyssey that transformed him from a confident engineer with dreams of Mars colonization into a humble explorer who understands the profound challenges and magnificent possibilities that await humanity among the stars. His journey from the familiar moon to the hellish surface of Venus, from the red plains of Mars to the crushing depths of gas-giant atmospheres, from exotic exoplanets to the nuclear furnace of our sun, has revealed the incredible diversity of environments that exist in our universe and the extraordinary adaptations that will be required for human consciousness to thrive beyond Earth. Through his eyes, we've seen that the path to becoming a truly cosmic species involves not just building better rockets or developing more advanced life support systems, but fundamentally transforming what it means to be human in a universe that operates according to physics rather than human desires. We've discovered that survival on alien worlds requires not conquest but adaptation, not dominance but cooperation with environments that challenge every assumption our evolution has built into our biology and psychology. The worlds we have visited together tonight have shown us that Earth is not just our home, but a miracle of cosmic circumstance, a delicate balance of atmospheric composition, gravitational strength, magnetic protection, and stellar radiation that creates the only environment in our solar system where you can step outside in your pajamas and simply breathe the air around you. This recognition makes our pale blue dot not less significant, but infinitely more precious. A cosmic oasis that deserves our protection even as we dream of expanding our presence throughout the galaxy. Our imaginary journey has revealed that the future of human space exploration will require advances not just in technology, but in consciousness itself, developing new forms of human identity that can maintain psychological health and cultural continuity while adapting to environments that have no precedent in our evolutionary history. The humans who eventually colonize other star systems might be as different from us as we are from our earliest ancestors, yet they will carry forward the curiosity, creativity, and courage that define the best of human nature. The challenges we have explored tonight are enormous, the distances vast, the technical requirements beyond anything currently available, yet the foundation for achieving these cosmic capabilities is already being established through the research, development, and exploration efforts that are advancing human presence beyond Earth's atmosphere. Each successful mission to the Moon or Mars, each new exoplanet discovery, each breakthrough in life support technology or propulsion systems brings us one small step closer to the day when humans might walk in under alien skies and call distant worlds home. As you drift towards sleep tonight, surrounded by the gentle embrace of Earth's atmosphere and the comfortable pull of familiar gravity, take a moment to appreciate the extraordinary privilege of existing during the early days of humanity's expansion into space, when our species is taking its first tentative steps beyond the world that gave birth to us. The universe awaits with wonders that we can barely begin to imagine, challenges that will test every aspect of human ingenuity and adaptability, and possibilities that could transform our understanding of consciousness, existence, and our place in the cosmic order. If these gentle explorations of cosmic mysteries have brought you comfort during the quiet hours, it would warm my heart if you could share a like and perhaps subscribe to join our growing community of curious dreamers who gather here each night to explore the frontiers of human knowledge and imagination. Your support helps this channel continue creating these peaceful journeys through the most fascinating questions that science has to offer. The stars that shine above you tonight are not just distant points of light, but future destinations for human consciousness, worlds where our descendants might build cities, raise families, and continue the grand adventure of discovery that has driven human civilization since our earliest ancestors first looked up at the night sky and wondered what secrets lay hidden in those mysterious lights. Remember that this exploration represents one perspective on complex scientific topics, and I encourage you to continue your own journey of discovery through the vast library of human knowledge that awaits your curiosity. The universe is far stranger and more wonderful than any single story can capture, and your own questions and interests might lead you to discoveries that contribute to humanity's understanding of our cosmic neighborhood. Sweet dreams of interplanetary adventures and cosmic possibilities, knowing that somewhere in the vast darkness beyond our atmosphere, worlds of unimaginable beauty and alien wonder await the arrival of curious minds brave enough to venture beyond the cradle of Earth and explore the infinite mysteries that fill the universe around us.